Hello, everybody. Hello, everybody. How are you? One, two, three, four. Hi, Taylor. Hi, Danielle. Oh, just here, Sana. If you're on YouTube, I just want to know who's watching. We'll get started in 18 minutes. In the meantime, I'll try to check on people's projects. Might as well check it. Oh, you know what I didn't do? I didn't post your practice exam. Let me do that quick. There it is. Let's move it away over here. Um, we're good. Hey, there's your practice exam. it's ready. I'll post it. Yes, that's correct. Problem set 9, we got through. If you look, I think number like 1, 15, and 21 are like the same data, and they do there's 3 steps. The first one is calculating A and B. We already talked about that. The second one is the SSE, SSR, and SST, and the R squared, and we talked about that. And today we're going to talk about T test and F test. So yeah, that'll be it. Up to speed. Sorry for everybody. If you're not on Slack, the question was, will the stuff we do today help with problem set 9? Hi, Leah. I'm sorry that you can't get on Slack. That's frustrating, but I'm glad you're here. Hey, Juan. Is that Juan? Cool. You're welcome, Taylor. Crazy, right? I don't know if this will work or not, but it's worth a try. So yesterday, I don't know, for those of you who are joining us, did you guys hear more about it? There's a boiler explosion, something like that, which meant I frantically had to figure out how to teach a class when I can't use the building. And our evening class, here I'm going to post practice exam. All the evening classes got moved to different buildings, and then the day classes, they're kind of like, oh, you guys just have to figure it out. You can cancel if you want, but we have an exam next week, and I was like, that's not a good plan. The evening classes got moved to Elvis, so mine was in Elvis, which I don't know if they have a whiteboard or what the plan is. It seemed questionable as a decision. Well, what are you gonna do? You do the best you can. You guys want to get exam prep materials? Wait, is this your section? Yeah, you guys are section 4. 2. Anyway, I'm sure some of y'all would have been happy to have class canceled, but I would have been disappointed. Hey, Deandra, I can see you. Although I will say it's pretty tricky. I have to remember all of you by your first initial last name, so it's a little bit of an IQ. How much can I remember? D. Fland, that's Deandra. Yes. I mean, I can show you. I'm working off the notes that are already posted. So for those of you who don't know, this maybe is a good time to show you. If you're in D2L, you can see it now, right? If you're in, this is my manager version, but if you go in as a student, which I can pretend I'm a student. Hey, I'm a student because that's how students talk. If you click in the content browser and notes, everything we cover in class is here, right? So today what we're doing is we're doing regression, simple linear. And so if you open this, I'm opening another copy. I don't actually need to download it because I already have it open. This is what it looks like. Let me go to the beginning. Oh, I don't know why this doesn't have a beginning page. It should have a beginning page. Maybe yours does and mine doesn't. No, it doesn't. Okay, it doesn't have a beginning page, but regression and what we covered so far is, you'll remember this stuff, right? We talked about what does it mean if beta is greater than 0? What does it mean if beta is less than 0? Beta is equal to 0. Hey, Brad. And so you can see the regression line and you can see the slope. But my notes are, I don't know, they're pretty good, I hope. But all the stuff I cover is in here, right? So I talked about the least squares approach. This actually goes a little bit more depth into the calculus of it, but it doesn't get really into calculus. And then you got your formulas here. This was the, Oh, this is yeah, I should fix this. This is not the numerical example that I use. Stop saying things to me, window. Hey, where did that go? Oh, here it is. This is a slightly different numerical example than the one we used. And so that's not the one that I'm going to be using in terms of the numbers. So you should take notes, I guess, but the math is the same. Maybe I'll just post the one that I'm using. Where is the one I'm using? Practice exam stuff. I don't know if that answers your question, but there's always notes posted. Does that answer your question? All these notes are posted. Because I don't feel comfortable saying, let me revise that. I'm somewhat hesitant to say anything to you guys without thinking about it first. Hey, whoa. In fact, without writing it down first. And so this is what I'm going to be covering today. I'm going to have this open on my window next to me. And here you can see this. Yeah, this has the numbers that match, right? This is what we did last class. I think we ended up talking about these assumptions right here. Cool. I'm glad that helps. But yeah, we ended up talking about those assumptions here. And so just so you guys kind of know what I'm doing while this is going on, I have two monitors. So you can't see my hands. Stand back a little bit. I have two monitors, one here and one. I'm terrible at this. One over this side. Okay, two monitors. The one right here with the video is what you guys can see, and then the other one on my right has like all of my notes and stuff that I look on. Now I've done this before in a very controlled environment where I'm recording a video and I'm going in and editing, and so like every time I clear my throat and I click and hiss, I can go in and like edit the audio. So this is going to be it's going to be a little messy. We'll see how it goes. But you can see that like there's a bit of a learning curve. I had to figure out how to, like I spent a lot of time figuring out YouTube live FAQs, like how do I start streaming? What are live events? And I've got a YouTube channel here. I can see you guys. Hey, there's 10 of you. That is not a good attendance. So hopefully we'll get a few more people. So I can see that. This is my the event channel for this thing. This is my Google Plus page. And so you can see, like, it took me a while to figure out like what the heck is going on. So I figured it out. It was a bit of a pain. I hope they fix whatever boiler problem they had and we can get back into our room. But in any case, I'm glad we live in the future so that we don't just have to cancel class. Or worse yet, like not have invented chalkboards yet. So we just have to talk about stuff and imagine an Excel spreadsheet in your mind. There is a bit of a lag, I think, right? So for example, I'm about to type 1, 2, 3. Hey, Leah. Aaliyah. Hey, Aaliyah. When will the practice exam 2 be posted? I believe it is posted now. Those people who got here a little early got to watch me do it. So let's see. I'm on as a student right now here. So if we go into the main page, content browser, exam prep materials, exam 2 now exists. And here you can see the practice exam with full solutions, the formula sheet, and the stat table packet, all the stuff that you'll need. And if you download the solutions, you can see, oh boy, I put a lot of time into these, so hopefully it's useful. What if it takes weeks to investigate the boiler issue? How would we take our exam 2? Hey, Robert, how's it going? Welcome. Hey, Laura, good to see you. What if it takes weeks to investigate the boiler issue? Well, to be honest, like one of the nice things about being not the president of the college is I don't have to know. Presumably, at some point, they'll tell me what to do. I'm a little frustrated, to be honest. I'm not brutally frustrated. I feel comfortable telling you guys. I'm a little frustrated that like they gave us no guidance about what to do today. So I think that's because they figured, one day of classes, we might have had a snow day. It's not the end of the world. It's not a big deal. We'll fix it. But if it turns out not to be the case that they can fix it, then they'll probably give me more guidance, and I'll be upfront with you guys about what that is. I guess to some extent, what if they don't? Depends on how well today goes. How will the exam go? Yeah, you know what, Sana? I'm just going to not think about that problem and hope it goes away. I find that as a life strategy, not thinking about things and hoping they go away, sometimes that's a good life strategy. Sometimes it's not, but sometimes it is. And I think this is one of those times. We're going to have the exam next week. They'll give us a room. You got to have faith. You got to have faith. Does that answer your question? The one thing I was going to say before I got that question, excellent question, Sana, was I kind of want to know how big a lag there is. So what I'm going to do to try to test the lag on how quick I see your question, how quickly I can answer it, is I'm going to type 1, 2, 3 into Slack and hit enter, and then as soon as I hit enter, I'm going to say 4, 5, 6. And if you guys could just like count like how many seconds, like thunder, if you could count how many seconds it takes between when you see the 1, 2, 3 pop up and when you hear the 4, 5, 6, I would greatly appreciate it. So here goes. 1, 2, 3, 4, 5, 6. All right, let me know how much lag we got. Ooh, somebody's typing. So that, okay. So was there some lag there? Is there lag there? Cool. Getting Aaliyah and Brad are responding. Awesome. Oh, Brad gave up. Aaliyah's back. Oh, several people are typing. Tell me who's typing. Not much lag? Awesome. That's great to know. Cool. Because I was a little worried. Because when I was testing the software, what I was doing was I was basically broadcasting to myself. And so it was like, it was going from my screen to the internet back to my screen. And I think that's like the maximum amount of lag. We'll see. I don't know. Cool. Hey, Aisha, you're here. Welcome. Never got the 4, 5, 6. Oh, I didn't type the 4, 5, 6. I said it on my video stream. So if Luke, if you're not seeing a video stream, then you need to go up, scroll up in general and click on the link. In fact, can I pin it? I wonder if I can pin this. Pin. Yes, pin this message. I'm not sure what that does. Oh, there we go. I pinned a message. So if you're not on the webcast, you can go there. It's also broadcasting on a Google Hangout, which means I think if you're there, I could hear your microphone and then I would just mute you. So that's fine. I can do that if I need to. But that's fine. I think it works okay on the YouTube cast. Yeah, it was a little bit of a crazy adventure because I was trying to use my tablet to do the writing, which meant that I had to like broadcast my tablet to the internet and then use my browser to pull it down from the internet. And that was really laggy and not pleasant. Hey, Samantha, welcome. It's good to see you. Cool. You get the message on Slack first. That's right. That's the thought. So I'll say 4, 5, 6 out loud. Okay. So I'm gonna write 1, 2, 3. Say 4, 5, 6. We'll do it again. 1, 2, 3. Enter. 4, 5, 6. So you shouldn't hear any lag in the audio because I'm just saying 1, 2, 3, 4, 5, 6. Obviously, they're connected. But between when you see me write something, like for example, see, I'll type. I am about to repeat this message aloud. Now, I tried to do that as soon as I hit enter. I started saying it. Hey, Will. Willie B 1, 2, 3. So I started saying it like right after. I'm curious just if there's a lag between when I type something and when. Hey, Katie, welcome. When I type something and when you see it, or when you hear stuff. If the only reason that lag would matter, because we're not doing like a voice audio back and forth. The only reason the lag would matter is if you guys try to stop me during the talk. Yeah, okay, slight lag. That sounds about right. For me, earlier it was pretty long. I think I shortened it. If you guys try to say something or stop me, I might not get them. I might have moved farther along, and so I'll just have to backtrack a little bit, however long the lag is. Okay, slight lag. That's fine. I think we can work with that. And hey, if it's terrible, hey, it's better than no class. We'll get something done. We'll figure out whatever we totally can't do. I don't know. I think we'll be fine. You guys tell me. All right, I got 10:59, so we're winding down on our time. Let's see who's here. I have 17 people here, which to be honest is probably about normal for on time for class. You can't hear a thing, Robert. I think everybody else can hear me, so I would check to make sure your speakers are turned on or your headphones are turned on or your YouTube volume is turned up. Or if you have a Q-tip lodged in your ear or chronic hearing loss from loud music. I don't know. I guess the short version is I think that's on your side. I'm not sure. Andrew, hey, welcome. Good to see you. Is it laggy in terms of jitter? Like, does it look jittery? Does it look okay? Hopefully it looks okay. I'm going to have to make your guys' window a little smaller so I can see my notes. Let's see if I can do that. There's my notes. Cool. All right, now I have 11 o'clock. Now, we might not go the full time just because we don't have to take roll, because as you guys are writing, I have your names here, so I know who is participating in this. I might do a roll call kind of at the end. You're watching on YouTube and chatting here. That's exactly what you should be doing, Andrew. Hey, Joshua, welcome. It's good to see you. You guys, if you're going to be watching on YouTube and chatting here, where here is should be general, hashtag general, because for some reason I didn't get those messages on general. Oh, there they are. They popped up now. Okay, well, yeah, watching on YouTube and chatting here is perfect. Okay, but I have 11 o'clock. Just to update those of you who just joined us, I just posted the practice exam before class started. Hey, I'm looking at the camera. I can see you. Hi, everybody. You can see over here is the outline I normally put up on the board. So hopefully that's useful. I'm going to hide that later so that we can see more of the board. But the part 2 analysis is due on the 24th. As I stated before, if the reason that you haven't worked on it or haven't made progress is because I haven't gotten back to you, which I think in this class there are 3 or 4 of you that I haven't gotten back to just because of time, because it's been crazy. We're hiring and traveling. I'll give you individualized extension, so that's not a big deal. Don't feel stress about it. We have till the end of the semester till it's really due, but I want to get the analysis part done. Problem set 8 you have, it's short. There were some people who had some confusion about whether these questions were just the same as questions that we already did. No, the data is the same, but in this case, they're confidence interval problems, right? So it's asking you to use kind of familiar circumstances and then answer new questions about it. Problem set 9 is due Thursday. Today's stuff should cover the stuff that you need to know for the rest of problem set 9. And then part 3 analysis I put up yesterday on D2L, and that's due in a few weeks, April 7th. So I would focus on the exam first probably, and then you should have time to focus on the, maybe take a look at it over the next couple of days, and then exam, and then back again. Any other questions? Oh, hi, Natalie. Good to see you. I hope you guys are doing well. I drove for, I talk about data. My wife and I left for a wedding in Brooklyn and Queens this weekend with the kids, which was crazy. We left Thursday. Let me see if I can pull up the data. So I don't know if you guys know, but Google tracks all of your, basically all of your movements, which some people find freaky, but I don't care. And so Google was able to keep track of like everything that I did. And for some reason, it's not responding. My browser's not responding. There we go. Google tracking. And so it kept track of how many miles we'd driven. And it turns out that over the course of 3 days, I think it was like 76 hours, we had driven for 48 hours. So that was pretty intense. Here I can show you timeline. Just, it seems data relevant. I thought you guys might be interested. But March, let's see, last Thursday. So this is what we did last Thursday. I know, it's crazy, right? So we drove from Atlanta to, and it doesn't even show, like I left GGC, drove home, drove down to Stone Mountain to get packed that car, drove down to Stone Mountain to get my daughter, the 1-year-old, and then drove all the way. Oh, that's okay. So we drove all the way to Richmond, but you don't see that because this is where midnight happened. And then you click over to Friday, and then you can see, okay, so we drove to Richmond, and my phone died there. That's why it's grayed out. And then we stayed at a hotel so we didn't crash into things. Then we drove from Richmond to New York. We got there, and you can see here that tracks on the left side. You can see 560 miles, 21 hours and 44 minutes. So on Friday, March 18th, we spent 21 hours and 44 minutes of that time driving. That is crazy, right? That means that we spent, for those of you keeping track, what is that? 2 hours and 16 minutes sleeping. Good times, good times. So that's a little crazy. Hey, Ton, welcome. And then Saturday was a relatively low driving day. We only spent 4 hours and 33 minutes driving around New York, which that is miserable, by the way. But it was awesome. We went to Greenwood Cemetery. There's a chapel there, which is just gorgeous for the wedding. My kids walked down the aisle. And then we went back to a place in Flushing called, it says MBS Love Unlimited, but it's actually a place called the Poppenhusen Institute, which I think was like an old mental hospital, but they turned it into like a place for weddings and stuff. And it's awesome because the groom is a musician. He's like a very successful, very talented musician. He's part of a group called what are they? Freestyle Love Supreme. He's a freestyle rap. Well, he mostly does music. He mostly plays piano and drums, and he's also a member of a group called Arthur Lewis and the Geniuses. But But the guy who wrote Hamilton the musical is a good friend of his, and like is part of his freestyle group. And so like they're really talented people. It was probably the best performance I've ever seen in my life at the reception. But my 1.5-year-old totally stole the show. She danced for like 5 hours. In any case, Sunday we got back in the car around 7:30 in the morning, 7:35, and then all the way till 10:47 when we got home. So a hell of a road trip. I'm glad to not be in the car anymore. So that's what was going on with me this weekend. It was so busy because the Mets weren't in town. People wanted to actually come. So yeah, it stinks because the hotel we stayed in was like one exit from Citi Field. I was a little sad. Like they could have got married in April. I could have seen a game. Oh well, it was fun. We had a good time. The kids had a blast, and we're hoping eventually we'll be able to send them up to stay with them for like a couple weeks. So see what New York is like when you get to spend some real time there. In any case, that's what I was doing this weekend. It was awesome, totally worth it. But man, I'm glad not to be driving anymore. How are you guys? What'd you do this weekend? You can chime in. We got a minute or two. People are still filtering in, I think, to be honest. Anybody do anything fun? Anybody drive more than me? No, didn't think so. Let's see, who do we have in here now? We're up to 25 people. That's probably comparable to like a day when people don't think there's going to be a quiz. Hey, Sophia, you worked, Willie. Was it good? Samantha worked. Yeah, good. Retrofit headlights took you 6 hours. Was that a fun 6 hours or a frustrating 6 hours? Played Xbox, Anna. Anything good? Henry really wants me to get the new Batman game, the Arkham Knight. I forget what the newest one is. Ooh, what'd you see? Did you see Zootopia? It's really good. You should see Zootopia. Cirque du Soleil. That's cool. Cool. Awesome. People having good times. That's great. I mean, and people who are working, generating producer surplus from their labor hours that they provide. The new Batman's good. So it would be for Halo 5. Cool. You got sound. Welcome, Robert. Hiking. It was a beautiful weekend from what I heard. Yeah, so the new Batman was pretty glitchy on PC when I was first going to buy it, so I was waiting for them to patch it and stuff. Hopefully they patched it by now. I usually wait for games to get to be $7. You moved to Atlanta. From where? Have you been secretly commuting from San Francisco? Cool. Long plot. Yeah, Henry likes to watch me pull guns out of the bad guy's hands with my, he's got the bat claw, the grappling hook thing. Henry, my son, really likes to see that work. Cool. Look at you guys all maximizing your utility through various choices. That's what I like to see. Work. Okay. Cool. I'm glad to hear it. If anybody else has more to say, feel free to drop in. But check out Paragon. Mobo. What does Mobo mean? How do I not know? I don't know what Mobo means. So see, I'm going to learn something. Shotguns. Oh, shotguns. I thought you were just like, okay, that's 2 words. You shot some guns. Cool. The YouTube page keeps dropping. Keeps dropping you? MOBA. Is that an online battle arena, multiplayer online battle arena? I'm going to guess that's what that means and then move on to things that we actually are here to talk about. Well, this isn't fun, though. Oh, cool. Cross-platform is always fun. Yeah, I usually play co-op stuff or single-player stuff my kids can watch, which are fun. The kids really get into it these days. There's some good puzzle games that they've really enjoyed. New York to North Carolina to Georgia to Florida, then back to New York. Hey, he made the opposite trip of me. That's crazy. That's pretty busy. Okay, cool. It's good to hear everybody's here and healthy. And by everybody, I mean most of you, and some of you or some lame people decided not to show up, or hopefully can figure it out. Actually, real quick before we get thoroughly enmeshed, let me just see if anybody emailed me to be like, I don't know what I'm doing. No, nobody said I don't know what I'm doing. Okay, cool. Maybe there are people who are lost, but if so, they have not found a way to tell me. Okay, cool. Let's talk about what we were talking about. We were talking about brushes. No, we were talking about the error term. Do you guys remember we had assumptions on the error term? All right, this is where we get to see if I can remember how to write with one of these things. Assumptions. The error term. You guys already have these in your notes, right? I think so. If I need to write slower or be more careful, let me know. But I'll say all the things that I'm writing, so hopefully it'll be clear. Assumptions on our error term. You watching your video while driving. That seems like a terrible idea, Deandra. You should stop watching and read the notes later and not get into a car crash and die. please. If that happened, like, we would be on the news. It would be bad, and also I'd be sad because you'd be dead. But also it would be on the news. So don't do that. Okay. And I hope you can blame your dad for your bad grade. It's his fault. Okay. Let's see. The assumptions we made on epsilon. The first was that I don't need that one. It was the mean zero assumption, right? I don't have to write all these, but I don't have to write the names of all of these. The expected value of our error is 0. That's another way of saying I'm writing expected value because, again, that's a little bit more like an operator. It does something to it, like a function. Another way of saying that mu epsilon is 0. Right now, again, that doesn't mean that that epsilon is 0, right? Or that there is no error. It just means that, like, if we tried to do like a plot of all the error terms, like, let's say we had 20 observations, and what we wanted was to plot the errors. What we would do is we put 0 in the middle, and we would expect sort of a distributed pile of errors around this, right? And that's what that mean 0 is saying. Just that the middle of the cloud of errors is at 0. So hopefully that's clear. The next thing we assume is that the variance of epsilon is equal to some value that we'll call sigma squared. And the key here is just that is true for every error. That every error, essentially these two together, say that every error is drawn from the same distribution. It is a distribution with a center at 0. Is this new stuff? Maybe this is new stuff. I'm pretty sure I mentioned the word homoscedasticity to you guys at the end of class. That sound familiar? It should be. It's either new stuff or review, but it's definitely the thing that comes after correlation coefficient. So Brad, you can just start writing it. Okay, so this assumption is called the assumption of homoscedasticity, which is a fantastic word. Hey, Jean. Just like that. If you ask questions on Slack, then I can answer those questions. So Jean just asked, for those of you who are just watching on YouTube and not on Slack, how do I... It's going to be hard for you to make sense of this if you're not on Slack because there's a lot of give and take, hopefully. But he was asking, how do I ask questions on the YouTube channel? And the answer is you don't ask questions on the YouTube channel. You have to switch over to Slack if you want to ask a question. Okay. Oh, you weren't there last class. Indeed, Willie. Indeed. Shame, shame. And now everybody gets to see me shake my head at you. Okay. Homoscedasticity. If you remember, we talked about briefly, I believe. It's your favorite word. Hey, Cooper. Welcome. It's a good word. Homo means same, right? Like homogenized milk. Or homozygotic, which I think is some bio term that I forget what it means, but like it presumably means. I think that must be identical twins. Hey, I just realized because zygote is like a little thing. Oh, you were volunteering. Oh, that's right. Okay, that's fine. That's right. I remember you emailed me about it. And then this means scattering. So that's what homoscedasticity means. It just means that every error essentially has the same chance of being scattered, right? They come from the same, the dispersion for each one when you're drawing it comes from the same thing. They're being drawn from the same bingo cage. I'm sorry, Willie. All right. What else? Those were our first two assumptions. And the first assumption is fine as long as you have a constant in your model. And if you recall, we do have a constant in our model. Let's draw our model real quick just to remind ourselves. Alpha plus beta x plus epsilon. This is our model. This alpha right here, this is a constant, and it absorbs all of the non-zero-ness. So that's an issue. It's possible in Excel and other software to prevent there from being a constant. But as long as you have a constant in your model, as we do here with the alpha, then the mean zero assumption has no problems. Homoscedasticity, on the other hand, is a big problem. And the reason that economists are really good at statistics is because it is a big problem, particularly in applications in the social sciences. And economists do a lot of social science statistics. And so we have got to deal with heteroscedasticity, which is the opposite of homoscedasticity. And if you take the econometrics class, which is after this, a lot of what econometrics is about how to deal with cases of heteroscedasticity. It also comes up a lot in finance, right? Because if you have companies, hey, I'm not going to that. If you have a lot of companies of different sizes, then the error terms on those are going to be drawn from different distributions. Okay, the next assumption is that epsilon I is independent. That is to say that knowing one error term doesn't give you any other information about any other error term. Independent. And so that's a new assumption. It's independent of xi as well. So it's independent of xi, meaning that if you knew your values of your x's, you wouldn't necessarily know the values of your error term. Now, why would that not be the case? This would not be the case, for example, if you did, let's say you did gift, let's say your y variable was your gift money, gift budget, equals alpha plus beta times temperature, degrees Fahrenheit, plus epsilon. Okay. Now, if you remember, I said that epsilon contains everything that is unaccounted for, unobservable, or noise or random. That's three. Yeah, three. Unaccounted for, unobservable, or random. And do you guys think that the temperature? This is what we did at the end of class. That's right. Do you guys think that temperature would have an effect on people's gift budget? Like, do you notice a relationship between the temperature and the amount of money people spend on gifts? Yeah, right. Why? Is it because cold weather makes people feel more generous? Totally, right? That's how I feel. Whenever I get cold, I think fondly of all the people that I care about. But no, the problem is that we have something that's unaccounted for right here, right? This error term is including things that are unaccounted for, like, for example, that most of the gift-giving holidays, Christmas included, Hanukkah included, Kwanzaa, there are a lot of them where people give gifts that happen when it gets cold, right? Particularly in the northern hemisphere. Now, you'll find that in the southern hemisphere, when it gets warm, people get more generous with each other. But there are more people who live in the northern hemisphere than the southern hemisphere, so that that's the weight of it. And so what's happening here is that it is not the case that this is independent of this, right? What we have is the temperature is related to things that are unaccounted for, and this is called, just so you know, this particular example is called endogeneity, and this is a really big problem, right? The bigger problem, a bigger example of this problem, is where we have like income equals alpha plus beta times education, because it turns out that when people decide whether to stay in school, it is based on, when they decide how much of this to get, this is a choice that they make. It is based on what the effect they think it's going to have on their income, which is stuff that shows up over here, right? So, for example, people who have very little education might have decided not to stay in school because they realize that education wouldn't benefit them, and that's going to have a problem because it's going to create an upward bias on this. It's going to say that education is worth more than it is, when it turns out that really what's happening is that people who will benefit from education rationally choose to get more education. And it's not necessarily the education that does it. It's the education combined with the personality type that makes education profitable, that makes education valuable, right? Like, if every time you see a number you want to punch somebody, you should probably not be in school, because like you're going to get arrested and that's going to hurt your income. That would be deleterious to your income in life. And so you would rationally choose to have a lower education because for you, it's increasing your income. But that's not a statistical relationship. I mean, that's going to bias the benefit to education. Okay. So that's an example of when epsilon's independence violation is, or independence assumption is violated. Okay. Deep breath. We got three assumptions: mean zero, homoscedasticity, and independence. The last one we're going to do is we're going to assume that epsilon is normally distributed. This one I used to have more of a problem with, but it turns out that as long as there's enough noise in the system, or enough different sources of noise, like say 30 different sources of noise or so, then the central limit theorem means that it will be roughly normal. But some people have a problem with it, particularly with small sample stuff, and so sometimes we get rid of it. It definitely makes it easier to do the math. It makes it so we could do next. What does that say after income? Income equals alpha plus beta times education. Yeah, I wasn't real careful about writing that one because that's one we've written before. So we've seen it before. But yeah, alpha plus beta times education. If you're watching your phone, some of this is probably pretty small. Okay. These four together, the reason we make these assumptions, you're very welcome, Samantha. These four together, the reason we make these assumptions is that they allow us to do some actual statistical inference, which is what we have not yet done. Because these four together imply that epsilon is a random variable with a distribution that is normal, with a mean of 0, and a variance of sigma squared. Okay, and so now what we have done is we have taken what we just called noise and kind of waved our hands and said, no, epsilon is a specific random variable drawn from a specific distribution with specific parameters. This means that we could standardize it if we want to. We can use a z-table and all that stuff. And more explicitly, if we look at our model, what we can see is that there's only one source of randomness in this model, right? Alpha is a constant, beta is a slope term, x is a variable, but it's not a random variable. And so this, epsilon, is where the randomness enters. What this means is that the only source of variance in y, comes from epsilon. That's where the jitter comes from, right? The dispersion. The variance in y is equal to, not equal to epsilon. It's equal to the variance of epsilon, which is equal to sigma squared. And then earlier, we already stated that we knew what the expected value of y given x was. You might remember this. This is the conditional mean function, or the regression equation. We said the expected value of y given x was alpha plus beta x. Let me see what that just... Is there a way to make the video bigger on your computer? Probably a full screen button somewhere on there would be my guess. Probably in the lower right corner of the window. It would be my guess. Okay, now this looks like a lot of math stuff, but what this does in terms of our ability to visualize and understand our data is really cool. So drawing straight lines is really tricky on this tablet, so you're gonna have to bear with me. Those are straight enough. Okay, so we were in a world before where we had a scatter plot. Come on, dots, there you go. Woo, look at all those dots. And all we were trying to do at first was just find a line of fit, right? We're trying to draw a line through these. Again, lines are hard to draw on here, but hopefully that's good enough. And that's somewhat satisfying, and we call that the y-hat, or actually that's this line right here. This equation right here is the equation for this line. But now, instead of visualizing it as a line, we now have some dispersion. Not only that, but we also have a distribution. And so what we can now say is that y is normally distributed with a mean of alpha plus beta x and a variance of sigma squared. What does this mean? Well, it means, and this is going to be a little tricky to draw, but I trust you guys can bear with me, is that instead of just choosing y sort of ambiguously, we now, what I'm drawing here is sideways normal distributions. Do you see the sideways normal distribution? We're drawing y from a series of sideways normal distributions on this curve. And so, that's a terrible normal distribution. Let me try that one again. If you want to know, let's say you have a certain level of education, and you want to know how much money you're going to make, this is your income. What I can now say is not just, let's say this is your level of education, then I would guess that your income will be this value here. But instead, what we can say is your income will now be drawn from this normal distribution, which I can now draw. Let me rotate it so it's a little bit more familiar. I can now draw like this, where the middle is at alpha plus beta x. And then our standard deviation is given by this value, sigma, right? That's the variance, so we get this standard deviation. And so now if you tell me that you have X years of education, now this is where your income is being drawn from at some random point in here. And that allows us to do a bunch of stuff that's similar to what we've already done. So hopefully this makes sense, where you can kind of imagine that what we have here is like you ever see those hills that are like flood hills on the side of like a soccer field or something, where it's just like a long horizontal, I think the word is berm. You ever seen a berm? Or a levee? Is that a word, levee? I don't know how to spell levee. But it's like a long horizontal mound that slopes down on each side, but kind of continues on. And now what we have, instead of just a straight line, is now kind of like a normal shaped tube that goes up along the expected value line. And that's really big because that gives us what we need to do to be able to do some statistical analysis. Okay. Okay, well, what kind of statistical analysis do we want to do? Well, the most important question we can ask ourselves when we look at our model, again, let me write it here, just so we can keep having it with us as I scroll through. Alpha plus beta x plus epsilon. The most important question is or are y and x related? Okay, so in my model, we have one parameter that determines whether y and x are related. What's the parameter that distinguishes the relationship between y and x? We talked about it before. It can be positive, it can be negative, it could be 0, and it's the one that decides whether there is a relationship or is not a relationship between our dependent and our independent variable. Do you guys remember which one it was? Pardon me? Yes, no. Now we're witnessing the lag time, which is more of an issue when I ask you guys a question. Yes, no. There we go. Okay, not sure. Good. Anybody else chime in? Which of the parameters in our model determines the relationship? Well, I draw a little int. There's no int, so okay. All right, we got a few people chiming in. Good. That's what I like to hear. Clouds. Several people are typing. Awesomeness. SSR SST thing. Okay, not quite. Good. That's the thing we had before. I'm talking specifically like looking right in here. Which part of this determines whether y and x are related? So when x goes up, what tells us whether or not y goes up or down? Y is a dependent variable. That's right. But we've got a parameter that quantifies both the size and the magnitude of, the magnitude and the direction of that relationship. Curious if you guys remember what it was. Yeah, so positive or negative. There we go. We got a few people there. The beta. Excellent. That's right. This beta here is the thing that tells us whether y and x are related. I ask that question and motivate you guys to think about it a little bit because in lots of scenarios, the question that we ask in English is, are y and x related? That's the question we ask in English. But the way we test it mathematically is we ask the question a little bit differently. We ask the question, does beta equal 0? Yeah, that's the slope. That's right. And what happens if beta equals 0? Well, if beta equals 0 to education, if we're doing beta times education, then that tells us about how exactly education affects your income. If beta equals 0, then it is the case that you probably should stop going to school because it's expensive and not likely to be worth it. And so that is the question that we're going to ask. The way we're going to ask that question is with what is called a t-test. We call this, right now we only have one regressor, but it turns out that as we get more regressors, we're going to have a t-test for every regressor. So this is a t-test of individual significance. Ooh, individual significance. And it's called a t-test of individual significance because we're looking at an individual regressor. We're just looking at x now. And if we had x1 and x2 and x3 and x4 and we had a bunch of x's, we would just be looking at one of them at a time. So we want to know whether that relationship has a significant whether that variable has a significant relationship with y. And by significant, I don't mean meaningful. Okay, significance in this sense has a very technical interpretation, which is that it has a sufficiently systematic relationship that we can conclude based on observing our sample that there is a relationship that exists in the population. That doesn't mean it's a big relationship, right? So let's say, for example, if you wear shoes that have laces instead of shoes that are like loafers or slip-ons or whatever, you get paid an extra nickel a year every time. Every single person who wears shoes with laces gets a nickel per year raise over people who wear shoes without laces. That would be a very significant relationship because it is a very statistically significant relationship because it's guaranteed, is 100% likelihood. It always happens. Everybody with laces in their shoes gets that extra nickel. Everybody who doesn't have laces doesn't get that nickel. But it wouldn't be economically significant. And so that's very important to keep in mind that when we say that these things are significant, we mean that the relationship is sufficiently systematic that we would reject the null hypothesis of no relationship. And that's what we mean by significance. Okay. So this is a hypothesis test. So we're back in the world of hypothesis testing. And so we're going to go back through the 5 steps. The first step for every t-test of individual significance is we are testing whether the slope term is equal to 0. Now later on we'll have more slope terms and we'll have to be more specific about which one we're talking about. But for now, we can just call it the slope term equal to 0. Our alternative then, you guys on the ball? What's the alternative going to be? I'll leave it open while the lag catches up. And when you guys tell me, I'll write it. Step 2, choose level of significance. We're going to go with alpha equals 0.05. And that's generally done. Most statistical software will go with 0.05. Yep, not equal. There you go, Luke. Thank you. All right, Willie. Cool. Pew, pew, pew. Everybody jumping in. That's what I like to see. Cool. So that's our alternative. And by the way, just to draw our attention back to that while we're here, before we move on to step 3, these two together mean, like this beta equals 0, this is not interesting in and of itself. What that means is that y and x are not related, right? But what does it mean if beta does not equal 0? What's the interpretation of that if beta does not equal 0? And again, I'll leave that question and I'll let the lag catch up so you guys answer as you hear it, and I'll chime in with the correct answer once you give it to me. All right, moving on to step 3. For step 3, we're going to choose a test statistic. That's S. Yeah, that's no, if we reject the null, that doesn't mean they're not related. The null means they're not related. What does the alternative mean? Choose a test statistic. Okay. So if we have a t-test of individual significance, Jean's maybe coming to the rescue. That's right. In this case, that's right, John. What that would mean is that they are related. The education is important. Now, if it's not equal to 0, it could be that it's significantly negative, in which case what that means is that, yeah, they are related. That's right, Taylor. Is that it could be negative, which is to say the more education you get, the lower your income. But we're doing a two-tailed test here, so we're concluding. We're just trying to see if we can conclude that there is a relationship. We're not talking about the directionality of it in this case. In some cases, you would want to be more specific about the direction, but that's fine. Okay, so to choose our test statistic, this is a t-test, and so this is our test statistic. We're not going to know all the parts of this, and so we're going to have to go down the rabbit hole a little bit to find out what they all mean. T equals B minus beta 0 divided by S subscript sub B. Okay. Now you can see that this is a pretty typical, it looks like a score formula, right? I mean, it looks like a t-score formula because we have a standard error in the denominator instead of a standard deviation, instead of a sigma. But we have a sample statistic minus a hypothesized value for a population parameter divided by our standard error. So that's a pretty typical t-statistic. And under the null, this has a t-distribution with n minus k minus 1 degrees of freedom. Now, I would like you guys to chime in with which parts of this you think we don't know yet. And I'll start by talking about the things that I think we do. But you let me know while I'm writing what you think we don't know, and then as I hear from you, as a lag catches up, I'll chime in. So we learned how to calculate b. To calculate b, we take the sum. This should already be in your notes, but this is the sum across all of our observations. Yeah, k, we don't know k yet. Okay. This is the sum across all of our observations of xi minus x bar. Thank you, Brad. Times yi minus y bar. K and S sub b. Cool. So you guys feel confident you know what beta 0 is, huh? What's beta 0 going to be? Divided by xi minus x bar, the quantity squared. S sub b is unknown. Okay. Chime in with beta 0 if you think you know that. K is pretty straightforward. K is the number of regressors in the model. And by regressors, I mean the number of separate explanatory variables. So if we're in simple linear regression, that means that k is always 1 by definition, because that's what makes it simple linear regression. But I'll give you a taste of multiple regression to show you when k would not be 1. So that would, in this case, k equals 1, because the model looks like this. Y equals alpha plus beta x plus 1, and our k is the number of these. Beta sub 0 is not the intercept in this case. In this case, so this is our regressor. This is why this is 1. Remember, beta sub 0 here, that's going to be our hypothesized value under the null hypothesis, right? So you got to look to the null to figure out what beta 0 is. This is plus epsilon, not plus 1. Sorry, it's epsilon. Let me fix that. Okay, so that's why k is 1, is because we have 1x. But let's consider a more advanced model, a more developed model. Let's say, for example, we had income equals alpha plus, so we did beta 1 times education plus beta 2 times, what else affects income? Age plus epsilon. Now, in this case, we don't have one regressor. We have two. We have education and we have age. And so in this case, k would be 2. And this is multiple regression. Okay? So k is the number of regressors. Still waiting on you guys for beta sub 0. Beta sub 0 is pretty easy, right? It's like mu 0. It's like d 0. It's like sigma squared 0. In every case where we've had a hypothesis test, we looked in the null hypotheses to find our value, our hypothetical value of the parameter, and that's where we got that from. So you guys get that to me when you can. You figure it out. All right. So we got k. Let's talk about S sub b. S sub b, that's the standard error. It's like the estimated standard deviation on our b term, or on our, on our sample, on our errors. So where does that come from? Well, that is going to be S divided by the sum, or the square root, sorry, the square root of the sum of our xi minus x bar, our deviation in x squared, our squared deviations in x, which still we don't know something. But this thing here, the denominator here, right? The denominator here, we've seen that before, because that shows up right here. So we've already calculated that by the time we've gotten here. So we can use that again. We'll plug that in. And that gets us a little bit closer, or one step down the rabbit hole to the other side at least. But now we don't know how to calculate S in this case. It turns out that S is equal to, let me make sure I'm getting this right. Yeah, I got it. S is equal to the square root of the MSE. And MSE stands for mean square error. Now we just need to know what the MSE is. Well, the MSE is equal to the SSE divided by N minus K minus 1. Whew. Okay, let's take a little breather because that's kind of a bunch of nested formulas. So now we should see things we know, right? You guys know what N is, presumably. We just learned that K is the number of regressors. Feel free. You guys can't nod your heads like you would in class. Yes, I know what N is. So feel free to chime in just to make me feel better about myself and about y'all. The SSE we learned about last class, right? That's the sum of square errors. And then once we have that data, then we can calculate this thing here. And then once we get that, we can calculate this thing here. And then once we get that, we can calculate this thing here. And then once we get that and beta 0, which I'm still waiting on from you guys, then we should be able to calculate what we need, our t statistic. Cool? All right, let's do a numerical example that we did in class. You guys remember in class, we did the example with the options and the change in sales. Well, we did that, and then we found a bunch of stuff. What did we find? We can write it over here if we want. So we had, let's see. There are a lot of steps. That's right. But as long as you have a bunch of formulas, you're kind of it's kind of like cooking a meal, right? First you got to dice the onions, and then you add some butter to the pan, and then you put the onions in the pan, and then once that's ready, you put something else in. Ultimately, like once you've done it a few times, you're just making food. But the first time it's a little tricky. Okay, so we got K. K is going to equal 1 because our model only had one regressor. It was percent options. Still nobody's sure on beta 0. So that little 0, remember, tells us where it comes from, that it comes from the null hypothesis. So what is beta 0 equal to? That's what I want you to tell me what beta 0 equals, right? Because the things we're going to need, actually, we can write the things we need now. We need B. We need beta sub 0. That's when beta equals 0. That's right. But I'm talking about beta sub 0. We also are going to need S sub B. And now we can start to work this out. Get it in Slack. Okay. Okay. So let's see. S sub B. Well, we know that's going to be. Oh, okay. Well, here's a big hint. I'll leave it there while I keep writing this stuff. We're going to need the value of sum of sub I minus x slash bar. Not that, x slash bar. Just a second. Okay. And then we're going to need n. I'm going to cue you guys in Slack to try to figure these out. You'll see them. What is the value of n in our teaching example? That we've been working on. Also, go back in your notes and see if you can find the sum of xi minus x bar. For that xi squared should be in the denominator of b. Also, we will need the value of b. Okay, so you guys take a look at your notes. We're going to try to do the numerical example, but I want you guys to try to find as much of that stuff as we can. And as I hear from you, I'll start plugging this stuff in. I already said K is 1. We're going to need to calculate. We already calculated B last class. Okay, 5 is n. Cool. That's what I like to see. Okay, so that's n. Keep them coming. You guys see the numbers I'm trying to fill in now, presumably. Lag's not that bad. We know that this is going to be the. Oh, we are also going to need the SSE. 0.2, that's B, right? Yeah, that's right, Cooper. So B equals 0.2. Build my little database here. Okay, SSE. You're covering it up with your wonderful messages. SSE is 90. Okay, cool. Okay, so now I can find the MSE actually. So you guys keep giving me more stuff if you can. Or is the only thing we're waiting on from you? We're still waiting on beta 0, which I had zoomed in real close here to give you guys a hint on beta 0. So the MSE is going to be SSE divided by, it's beta sub 0 is the value of beta under the null. I'm getting a little anxious, but I'll just tell you in a few minutes that we can't get there. So MSE is going to be SSE divided by n minus k minus 1, which is 90, divided by 5 minus 1 minus 1. It is 0. Yes, ding, ding, ding. Winner, winner, chicken dinner. All right, 0 here. That's right. Because that's, and where? How do we know that? We know that because right here, these numbers here, these are beta sub 0. Cool? Cool. Hopefully the emotional anguish of the last 2 minutes, 4 minutes have really embedded that in your brain. Excellent. Well done. Okay. Okay. What else? Oh, so what's the MSE? Well, the MSE is going to be 90 divided by 3. So if you guys want to hit me back with what that is, that would be good. Calculators, people. Cool. All right, so we've got 30 there. Awesome. It's like a roll call. People are like, yes, I know how to divide that. Awesome. Great. Okay, so now we've got our MSE. That means we can get our S. Because if you recall, S is going to be the square root of the MSE. I don't have that open, so let's see. You guys tell me, what's the square root of 30? Tell if I want, but you guys are here. That's what I have you for. So square root of 30, let's see, that's 25 would be 5. 36 would be 6, so it's going to be 5.5 probably. So I'm going to guess 5.5, 5.5. You guys tell me if that's right. 5.477, 5.478. We'll go with 5.48. Oh, that's not, no, it's not the square root of 5.48. It's the square root of 30, which is 5.48. Cool. So now we've got our S. I still need this thing. What's the sum? So let's see. Let me pop that one up again. Copy link. There we go. Paste. Anybody find that one yet? The sums? That's where we're stuck right now. Is this one here? If you remember, if you look back in your notes, you can see it's right here, right? So this thing here is what we're looking for in your notes. Yeah, if you remember when we calculated B, the way we got 0.2, good job, Taylor, was we calculated that it was like 800 divided by 4,000. And so that's where that 4,000 came from. Okay, so that means the sum of this thing is 4,000. Let's look back at our formulas again. Now that means we need the square root of that, right? So the square root, copy this. Square root. You guys tell me the square root of 4,000. There we go. Square root 4,000. That'll give us the last part we need. 63.245. Take your word for it. As soon as we get somebody else to agree with you. Cool. Awesome. Okay. Now we should have all the stuff we need. Let's zoom out from the board a little bit so we can see what we need. So just to recap, what we're trying to calculate is, now that we've done all this stuff, we'll write it down by hand. We're trying to calculate our t-statistic. It's going to be b minus beta 0. A little bit more legible. Divided by s sub b. Yeah, we're almost done. We almost got s sub b. Now we know that b is 0.2. We know that beta 0 is 0. And now we just need to get s sub b. Well, s sub b equals s over the square root of the sum. That's not quite s sub b. That's close. We got to still have to calculate xi minus x bar. I'm just rewriting this stuff, so if it's a little blurry, just look at your notes from a moment ago. And now we know that s was the square root of the MSE, and then the MSE was the SSE over n minus k minus 1. Cool. Thank you guys for getting ahead on the calculations. That's great. This looks like it's going to be 90 divided by 5 minus 1 minus 1, which is 30. And that means that this is the square root of 30, which you guys told me means that it's 5.48, which means that when we go up here, we now have 5.48 divided by the square root of 4,000. And we got that from somewhere else, right? We got that from a previous class, but we could do it with the original data. We would need the original data to calculate this, just to be clear. This is 5.48 divided by 63.25. And then Robert is telling me that's 0.0866. I'm tempted to take his word for it, but I think I'll show you anyway. 0.08. Brad agrees it's 0.0866. Hey, I calculated it earlier. What do you know? 0.0866 it is. Here's my little cheat sheet that I made in case I need to calculate it. Cool. We are in broad agreement that it is 0.0866. That is what I like to hear. 0.0866. Okay, so going up here now, that's what goes here. 0.0866. Somebody calculate t for us while I continue to write this. Numerator. I'll do the numerator. That's 0.2 divided by 0.0866, which is going to give us a t-statistic of, that's 2.4, 2.2, 2.3. Do you know where they're coming from now? 2.309. Okay, 2.309. That's good. I hope they're clear from previous classes, Willie. That's where they're coming from. 2.3095. Uh-oh. That means we're rounding wrong. Let's calculate it using Excel. Let's see. We've got, I didn't put 0.2 here because that's our B. But now we can do 0.2 divided by 0.086603. 2.31 is what I get here as well. So 2.31, if I expanded that, 2.3094. 68822. You rounded clearly because I'm getting a different answer. Have you no standards, Cooper? Okay, 2.309 is fine. So 2.309 is plenty. That's our t-statistic, right? And that's the end of step 4. So just to kind of draw, like to review, to scroll up here. Step 1, state our hypotheses. Step 2, choose a level of significance. Step 3, choose a test statistic. And then just to explain the test statistic, there's a bunch of stuff that we had to do. But then to calculate the test statistic, we kind of work our way through until we get to kind of first principles. And then if you kind of look, you can see we kind of stair-stepped our way. We started here, right? This is where we got to stuff we actually knew. And then we kind of went up to here, and then up to here, and up to here, and now we're up to here. And so that's kind of, you work your way backwards. And it takes a little doing, but it's not brutal. It's kind of like a Sudoku, right? You're kind of working your way logically. Okay, so now we have a t-distribution. How many degrees of freedom do we have? Well, if we look up here, we can see n minus k minus 1 degrees of freedom. Okay, And if we go down here, we already calculated n minus k minus 1 right down here, right? Oh, I'm trying to draw on my actual screen. I need to draw my tablet. N minus k minus 1 is 5 minus 1 minus 1, which means we have how many degrees of freedom? For those of you waiting for the easiest math problem of the day to chime in on, you just had your opportunity. There you go, Cooper. All right. So we draw ourselves a t-distribution. T-distribution has a mean of 0. And we've got 3 degrees of freedom. And I scrolled past it up there, but it's still over here in my Excel spreadsheet. So I can write myself a little 2.309 here. Cool. And now, because this is a two-tailed test, here you go, Robert, nicely done. Because this is a two-tailed test, we need to find this area. We need to double this area for our p-value. How do we do that? Well, we go to our t-table. Double this area. That's a little hard to read. Okay, cool. 3, yes, excellent. So we got to find that area. How do we find that area? Well, we need a t-table. Here, I'll write it down here so it can be very satisfied. 3, and that's where this number came from. For those of you who are like, why did he write 3 there? It came from right there. Because that's n minus k minus 1 degrees of freedom. Okay, so now we got to go to our t-table. I think I have it open already. I do. Hey, now you can see it. Well, that's a standard normal table. So let's go switch pages to one. There's a t-table. All right, and you should see here, we got 3 degrees of freedom, right? We're looking for 2.309, and I see it here, okay? You guys see it here? Go down to 3 degrees of freedom. We're looking for 2.309. It's right in this area right here, right? In between 1.638 and 2.353. So those are the neighboring values. Make sense? Let's move this over a little bit. 1.638, 2.353. Yeah, let's move it over here. Hey, stop it. All right, good enough. Okay. So now we're drawing our picture. Let me draw it a little bigger just so I don't screw it up. It's a little easier. Yeah, that's right. Yep, 10.10.05. That is the worst t-distribution in existence. Let's try it again. It looks like a gravel mound. Okay, so we've got a t-distribution, 3 degrees of freedom, test statistic at 2.309. And then we've got neighboring values of 1.638. That's this one over here. And then we've got 2.353 over here. And then as Samantha pointed out, 2.353, that gives us an area over here of 0.05. That's from right here, right? Hey, Dragon. Dragon can't hear me. Hey, Dragon. He's from the other class. Check your email and Slack and D2L for a web link. Sorry about that. We got interlopers jumping into our hashtag general from the other quant class. All right, 1.638 gives us an upper tail of 0.10. And so our area is between 0.10, because that's bigger, and 0.05, because that's smaller. But that's not our p-value, right? What do we have to do to calculate our p-value? While you do that, I'm going to try to calculate this area in Excel to make it exact. So let's open up Excel. We've got 5 minus 1 minus 1 degrees of freedom. So that's my degrees of freedom. Now let's see if we can do our upper tail. Our upper tail. That's going to be equals t dot. That's right. We're going to have to double it. So we'll double that. Okay, hold on one sec. It will be a webcast. Go to a computer. Okay, sorry about that. I should just be ignoring people probably from other classes right now. 0.1 is less than not alpha. I think you'll be able to refer to this webcast later. If not, I don't know. It's kind of like class. is in D2L. Okay, I'm going to ignore him. T.dis.rt. My X is my T statistic here. My degrees of freedom is that right there. And we can see that this is the size of the right tail, 0.05. But that's not exactly correct. If we paste it here, yeah, it should be p-value. That's right. You can see 0.052044 is our actual size of our area, which you can see is indeed between 0.05 and 0.10. But we need to double it. So we multiply this by 2, multiply this by 2. And as you guys say, we get 0.1 over here is less than our p-value, which is less than 0.2 over here. And then if we want to be precise, our p-value, or more precise since we have access to Excel in this moment, we can take this and multiply it by 2. Again, that's just showing me just the first digit, whatever. And it turns out that the p-value is 0.104. So what's your conclusion, guys? We got our p-value is 0.104. We had an alpha of 0.05, and so now we have to draw a conclusion. Where's alpha go? Alpha was 0.05. So let's see. That means that it's going to be over here. That's our alpha. Fail to reject. Reject. Okay, so we've got some disagreement, Luke and Warner. Okay, so far we're at 50-50 in terms of votes for rejecting and failing to reject. Cool. Cool. Okay. Anybody want to cast the decisive vote? Well, what we're saying, let's think about this intuitively again. Okay, Samantha's coming on the fail to reject side. What we're saying is, what is the chance that we would see a sample like this if there really was no relationship? What is the chance we would see a sample like this? It turns out that the chance we would see a sample like this is about 10.5%. And we said that if it was less than 5%, we would reject the null. But in this case, it's in fact greater than 5% by kind of a lot. And so this implies that we fail to reject the null. Because p-value is bigger than alpha. Whenever p-value is bigger than alpha, we fail to reject the null, which means that we are going to maintain the case that beta equals 0. P-value is less than 0.5. It has to be less than 0.05, because what you're saying there is less than 50-50 chance, right? And so we're comparing to, we're never going to have an alpha of 50%. We'll have an alpha of 5%. So we're failing to reject the null. And remember, that means that we're gonna keep, we're gonna maintain our belief in this. And what does this say about our original model? Let's look at our original model again. Our original model was that your change in sales was equal to alpha plus beta times percent options. That's right. It does not mean that. That's right. It does not mean she has accepted you. That's right. So we're not actually gonna accept that beta equals 0. What we would probably do is say, what did we miss? Did we miss something? Is there something going on here? Maybe there's not a relationship. Tomato. I don't know if tomato is a word. They are wise words, I think. So what does this mean about our relationship between our thanks a lot, Cooper. You threw me off my game. Between sales and percent options. What can we say about that relationship? What would we go back to people who think like, you know what you can do? You can boost your company's value just by changing your CEO compensation structure. And so the board, I guess, is the one that decides. What do you guys think about that idea based on this result? If we fail to reject the null. Well, I probably wouldn't get too serious about it. Right? So think about that for a minute. But I probably wouldn't get too serious about it because if you remember, our sample size was 5. Which is to say, like, if I were you, I probably wouldn't get all worked up about any result. That's not 5 factorial. That's bad. I don't want it to say 5 factorial. I just meant that, like, it's 5, like, Shake my head. Is that what you guys say? Right. You don't want to. You don't ever want to base your company's decisions based on a result of 5 companies that you've looked at. That's just not enough information to draw reasonable conclusions from. Hopefully you guys know that. Hopefully that's clear. That n equals 5 is not enough. Not to mention it's made up data. But in this case, what we have is we just have a weak enough relationship that we can't draw strong conclusions. Yeah, you need a bigger sample size because what's going on here? I mean, it's possible that there's not a relationship. In principle, you wouldn't think there'd be a really strong relationship, but it's possible that there's not a relationship. But we're just missing it. All right, let's look at one other type of test while we're here. We've got 10 minutes, and we'll lay out the steps for it. It's not super complicated. This will be more important when we do when we get into multiple regression, but I want you guys to see it now anyway. It's called an F-test of joint significance. And it's like a t-test, except it's testing all of the x's simultaneously. Shaking my head is correct. Significance. Kids these days with their lingo, their newfangled lingo, it's so hard to keep up. Always Snapchat and what have you. F-test of joint significance. Okay, so we've got our null in this case is always going to be that all the coefficients, all the betas, are equal to 0. Now, we only have one beta right now, but later on we'll have more. The alternative is that at least one beta does not equal 0. And that's what we mean by joint significance. Essentially, what we're doing in this case is we're testing the entire model. Right? So we're trying to see, does this model have any predictive power at all, right? So for example, you might want to know if knowing something about the cartoons that somebody's kid watches can be predictive at all of whether they're going to spend money on your cereal or something like that. In that case, you might, you have a bunch of different cartoons and as dummy or as categorical variables and test to see if any of them have any predictive power at all. Step 2 is to pick a level of significance. Step 3 is going to be to choose a test statistic again. The test statistic in this case is an F statistic, and it is equal to the MSR divided by the MSE. It's pretty straightforward. Under the null, this has an F distribution with k degrees of freedom in the numerator and n minus k minus 1 degrees of freedom in the denominator. So let's talk about the MSR. The MSR is the mean square due to regression. It's kind of like the MSE, but it's the other side. And it's pretty simple to calculate. It is the SSR divided by K. So going back to the stuff that we needed for our little database here, where was that? Here we go. We already have K. We already have the SSE. If you remember, the SSR was, what was the SSR? The SSR was 160. Okay, I'll just give that to y'all because we're running low on time. We'll tidy this. We'll finish this up. So we've got our SSR divided by K. That's going to be 160 divided by 1, which is 160. And then if you guys remember from above, our MSE, we calculated to be 30. Oh, and it's right here, right? 222, 30. So that means that our F statistic is 160 divided by 30. You guys want to chime in on the value of that? Go right ahead. In the meantime, I'll draw the distribution. So what we have is an F distribution. That's step 4 done as soon as you guys give me the answer to that. We've got an F distribution. Oops, there we go. Which looks like this. Wow. And it's got k degrees of freedom in the numerator. There you go, 5.33. Joshua gets the prize. 5.33. Nice try, everybody else. You already got it. Okay, so we've got 1 degree of freedom in the numerator, 3 degrees of freedom in the denominator. And then over here we have, let me scroll down a little bit so I can write 5.33. I believe these are always upper tail tests, but I'll confirm that once we take a look at the p-value. So I believe that these are always upper tail. Which means that this should be our p-value. So if you guys have your F table, now's the time to get that out. some consensus on our division, if not our ability to reject or fail to reject the null. Cool. Okay, so let's scroll down. I got my chi-squared table here, and here's my f table. It's a little tricky to see, but you can see it. Our denominator degrees of freedom is 3. Our numerator degrees of freedom is 1. And so we find ourselves right here. See this? Hey, that's handy. It shows up right here. So we're looking at these numbers right here. 1 degree of freedom in the numerator. In the numerator, 3 degrees of freedom in the denominator. And again, 5.33 is on here, but you can see that it's larger than the largest value here, right? Or it's small. I'm sorry, 5.33 is smaller than that, which means that our p-value is going to be larger than 0.10, because wherever it is, it's up here, right? It's above this 0.1 line. Not by much. You can see 5.54 is close, but it's above it by a little bit. And again, if we want to be more precise, Excel has formulas that can tell us this. So let's see. We had 160 was our SSR. So our F is going to be 160 divided by our MSE, not SSR. That was our MSR as well. So that's our F statistic. Degrees of freedom in the numerator was 1, and degrees of freedom in the denominator is already up there. So here we get our p-value. F.dist.rt. You can see it says returns the right-tailed F probability distribution for 2 data sets. My F statistic is there. Degrees of freedom in, no, it's not. My F statistic is there. Degrees of freedom in the numerator. In the numerator, degrees of freedom in the denominator. I've got 0.1. You can see that the p-value is exactly the same. So 0.104088. And it turned out if we made that wider, right? So if I just made that wider, as wide as I want it to be, it's the same to however many digits you want to make it. Because it's exactly the same null hypothesis. It's exactly the same question that we're asking. As we get to multiple regression, it will not be exactly the same. It's exactly the same right now because our t-test of individual significance is testing the value of beta, and our f-test is testing the value of beta. But if we have 2 betas, then we'll have 2 t-tests and 1 f-test. And we'll talk more about that next class. Okay, now the cool thing about these tests and about all the stuff we've done, right? We've calculated B and A, we've gotten a line, we've calculated the R squared through the SSR, SST. Oh, I forgot to finish this. Same thing as before. Failed to reject. The end. Okay. We calculated the SSR, SST, got ourselves an R squared and then a correlation coefficient. We talked about some assumptions so we could build some statistical tests. Every time anybody runs a regression, they basically want all of this stuff to happen. And so Excel makes it very easy to do this stuff. We'll begin next class by looking at Excel and how it works to do this stuff. But just so you know, right here where it says data analysis, this gives me all of the things that I need to run a regression. So I can show you how quickly. We've got 3 minutes, and I don't even have my data in here. I can enter my data and run a regression before class is over. So let's see. We had, that's not the real data, is it? That's not the real data. Where's my data? Data. Here it is. Percent change in sales and options. Copy this. Put it right here. Oh. Not sure why that's so big, but there's my data. If I run a regression, go to data analysis, regression, click OK. My Y's are changes in sales. X's are these. We'll go through how this works in class next time. But I just want to show you. Click test. There we go. It automatically calculates all this stuff. So you can just kind of soak this in. Remember we said 5.33333 was our F statistic? Hey, that's right there. Remember we said our T statistic. You guys said it was 2.309. If I scroll up in Slack, I can see 2.309468822 to get weird is what Coop said. It turns out it's 2.309,401. Our p-values are given automatically. Our B is calculated. Our n minus k minus 1 is calculated. Our k is calculated. Our s is calculated. MSR, MSE, SSR, SSE, SST. All that stuff is calculated automatically. So sad news is we did a lot of work that Excel could do for us much more quickly. Happy news is starting right after the exam. I mean, next class, we're going to learn how to read that output, right? Because I don't know how you feel about that, but it looks a little crazy to me. Starting next class, we're going to learn how to read this output. And then starting after the exam, we're going to spend almost all of our time letting the computer do the arithmetic, and we'll talk about how to get meaning out of this. Cool? Cool. That's 12:15. Nice work, guys. If you have any questions, I'm going to be hanging out on Slack talking to you guys for another 5-10 minutes as needed to answer any questions. And then I have another class at 12:30, so you guys have to leave. But this webcast, if you want some review on statistics, you want to see what BOSA 2000 is like, you're welcome to hang out and watch. Thank you, guys. I hope this was okay. If you have any feedback, you can feel free to post it to Slack or email me or private message me on how you think it should go in the future. But I'm grateful for you guys hanging in. I hope this was an adequate substitute for a 1 day off when we couldn't use the building. Cool. Cool. Thanks, guys. And Sana, you had a question about whether we'd have access to this. I don't know. It's the first time I've ever done a live webcast, but I'll let you know once I find out what Google does with these videos. I'll let you know what happens. Okay. Thank you, guys. Bye. Hey, Delma, welcome. Get me back up here. All right, let's see. Today is. Hmm. Sana, I want. All right. Okay, so if you guys can hear me, then that means you're here. You want to be on Slack if you can, because that's how I can hear questions from you. Let's see who's on right now. Right now, it looks like there are 13 people. So we're getting people who are on the site. That's good. But be better if we got more people. But yeah, come on Slack. Check in there. Just say hi, whatever, that you're here. And that's how I'll know. That's how I'll know that you're here. Let's see. My phone is in good shape. Hashtag general is where I've been fielding questions. I just did this with my quant class. And it worked pretty well. Can y'all can hear me? Did I unmute? I did unmute. That's smart of me. Hi. Excellent. Hey, Delma. Yep, I saw you, Delma. David, good to see you. Cool. Luisa's here. Brandon's here. Just curious. Hey, Anisha, Eli, Ray. Are you guys on campus or are you at home? Just kind of, how are you getting access to this? You're here. Becca's here. Okay. There's a little bit of a lag, by the way. The way I worked this out last class was I asked questions at home. Cool. And then kind of cool. Lots of people at home. So people coming from home. On campus student center. Okay. Hopefully you're able to get in there. Home. Hopefully you guys are benefiting from being able to do this from wherever you want. I feel like it's a little disadvantageous to have to do this compared to being in the classroom. It's not quite the same as in person. But I also think it's a pretty decent substitute. I guess you guys will have to be the judge of that. Just so you know, the way that I worked at last class, when I was working with that class was, I should note this here, was I'd ask a question and then sometimes I'd spin my wheels or talk about something else for a minute while I waited for the lag to catch up. Good to know, Shrees. While I waited for the lag to catch up for you guys to answer my questions. We have an exam a week from today. Anything else due from me a week from now? How do you guys feel about it so far? I mean, just a little feedback. Are you glad to be able to watch this from wherever? Hey, Shivam. Would you like to do this sort of thing more often? I'm curious. Maybe you should ask after the fact, but just sort of prospectively, does this seem like it would be a good way for us to communicate, for me to broadcast over YouTube? You guys can tell me how bad my handwriting is later. Okay, so it does seem useful. Good. I have considered trying to teach this class as a hybrid class. Sometimes because the videos are helpful. We have the videos, and then this kind of live casting thing works pretty successfully. I think I'm pretty tech savvy. Yours is blurry when you try to make the screen bigger. Does anyone have that same problem? The reason for that is probably your resolution. That's probably based on a combination of my upload speed and your upload speed. Hopefully that's okay. I guess the bigger question, the question of whether it's too blurry is, can you read this stuff in this window here? The text that I'll be using is probably a little bigger than that, but if you can't read that stuff, then you'll be able to read my handwriting. I'll write big. Ooh, you subscribe to my YouTube channel. Woo, yes. But yeah, it's occurred to me. So you can't read that. Okay, so a few people can't read it. Can anybody read the outline to the left here? Campus internet on point indeed. Hey, Ajwa. Indeed. Well, at least we're not in a building that exploded yesterday. Will you be able to rewatch once this is over? I believe so, Charisse, but I'm not totally sure. The things that it says over there. Yeah, I got it. The things that it says over there. Okay, so other people can. That means that it's on y'all's side, and it probably has to do with your resolution. Wait, what? Oh, shots fired. I hope you mean metaphorically. Got to be careful when something exploded yesterday. Although from what I heard is just a boiler. Please make it a little bigger. If I make it there, I can make it a little bigger for now. Yeah, I don't want to cover. Okay, so this is just the outline that I put up on the board every day, right? So that's what I have here. What's due dates, stuff like that, as well as what's gonna be covered today. Is that better, Ajwa? Who else was having trouble? Dalma and Anisha. Hopefully that's a little bit better, and you can kind of read what it says. Oh, no quiz today. It's clear now that I enlarged the font. Okay, well, I'm going to hide it in a minute anyway so that we can actually talk about and do stuff. But I just wanted you guys to see that kind of as people are settling in. Oh, I have 12:33. It's time, huh? So we can just, we're not going to have a quiz today. We probably will take the whole time. I wasn't sure I was going to with the last class, and then I ended up taking the whole time anyway. But anyway, I want to check in with you guys. I want to show you, this is not totally unrelated. It is statistics related, data related. But I wanted to show you my weekend. Somebody on Facebook was freaking out because they're like, do you know that Google tracks your every move? And they were freaking out. And I was like, that's awesome. That's what I want. What I want is to have every move of mine tracked, because then I can share things like what I'm about to show you, which I think is pretty awesome. Y'all can tell me whether you think this is awesome. So if you do go to Google location, if you have an Android phone, I don't know if this works with click the setting button and raise quality settings. Yeah, what Jenna said. In the bottom right, you should have a little gear. Part 2 and Part 3 analysis. Yes, that is the project. So Part 3 is now due on April 7th. So I announced the due date on Slack. And if you're working on Part 2, we can switch back to that for a second. I'll tell you about my weekend in a minute. If you're working on Part 2 and you're waiting to hear from me, which I think like 4 or 5 of you are, I'm sorry. That due date does, individual extensions will be given as needed. And that's not the hard deadline in the sense that the end of the semester is when the full project is due. But I'll work with you. I got a backlog, and I'll show you in a second why I have a backlog. I've had a busy couple weeks. We're hiring people. I have been made the point of contact for the study abroad program. I am also the point of contact for our corporate sponsorship program. I got a lot going on. But in addition to that, I had an awesome weekend. Went on Thursday. Let's see, when's Thursday? Thursday was March 17th. You can see how I spent my time, because apparently Google tracks me everywhere I go. You can see that on Thursday I spent 9 hours and 34 minutes of my day driving, which is a lot of time. That some of that is commuting to work and stuff, but starting at if we scroll down here, you can see at 3:09 I left GGC. I drove for an hour to get home, and I was at home for like an hour. And then I drove for 2.5 hours, stopped for gas for 9 minutes and get the kids ready for bed. And then drove for another 4 hours and 25 minutes. And that ended up with us in North Carolina. But what you don't see is that I wasn't in bed, because that's the highway, if you can see. Like, this is just on the highway. That was just when midnight flipped over. And then we click over to the next stop, or the next day, and you can see it picks up exactly where it left off on the highway. And then we drove all the way to Richmond. And then you can see, actually, this is the big number here, right? On Friday, look at the amount of time I spent driving on Friday. I spent in the car. 21 hours and 44 minutes of Friday I spent in the car. That's crazy, right? I feel like that's a little crazy. You guys can tell me if you think that's not crazy. But that, if you want to do the math, that means I slept for 2 hours and 16 minutes. That's not true. I slept a little bit in the car because my wife was driving and we took turns a little bit. But yeah, so we drove all the way up to New York. You can see we stayed at Hotel de Pont in Flushing. We got there, then we had to drive to Brooklyn for lots of coffee. Y'all think we're crazy. Lots of coffee. It thinks I was on a bicycle here. I was not on a bicycle. So we went to a wedding rehearsal here because my kids were in my friend's wedding. And then we went back to their house in Flushing, which I think is over here somewhere. I don't know, somewhere in here. And then went back to Hotel de Point. Or no, maybe they're over. Yeah, I don't know where they are. In any case, that was what we did Friday, rehearsal. Saturday, you can see I spent some time walking around here. I walked the baby in the stroller. That's what that is. So we went for a walk. Oh, and then I walked to Rite Aid. And then we went to the wedding. Kids were in the wedding. It was awesome. And then we went to this weird place for the reception. It's called the Poppenhusen Institute. I think it's an old mental hospital that they turned into like a place where they do receptions and stuff. But it was awesome. So we're good friends with both the bride and the groom. But the groom is a musician. He's like an amazing performer. He's a freestyle rapper and musician. He's like the front man for a band called Arthur Lewis and the Geniuses. They do like R&B and jazz and stuff. And he's part of a group of really talented people called Freestyle Love Supreme. If you're ever interested in watching people, they do this amazing like audience participation thing where they have the audience just yell out words and then they freestyle rap to get them to work those words in, like an improv thing. It's crazy. It's very cool. But it was probably, like, as far as the reception goes, like the best musical performance I've ever witnessed in my entire life. So that was amazing. And the crazy thing is my 1.5-year-old, she totally stole the show because she danced for 5 hours straight. I think it's 5 hours. Am I exaggerating? We can fact check me here. I didn't go to Buffalo Wild Wings. I went here from, it thinks I'm like all over the place here, but we got there around 8:57 somewhere. and left at midnight. Maybe it was 4 hours straight, 3 hours, 4 hours straight. But in any case, my 1.5-year-old totally wowed them. Oh, and then we took pictures. This was my daughter with the creator of Hamilton, the musical, who she's a really big fan of Hamilton. Oh, and you can see my son fell asleep in the corner. Okay, not vacation photos. But yes, it was an awesome trip. And then Sunday, we drove all the way back. 822 miles, 14 hours and 16 minutes of driving. So overall, I figured it out. In about 76 hours, we spent 60% of it driving over the course of the weekend. So statistics, right? Pretty cool. You can quantify your experience of life. Google knows. That's right. I'm totally fine with that. I don't know why people are freaked out. I, for one, welcome our robot overlords. I don't know what problem everybody has with it. Cool. Okay. How about you guys? What'd you do this weekend? Jump in. I'm curious. Did anybody work? Did anybody travel? Anybody drive as much as I did? To be fair, and in all honesty, I did almost no driving. I drove for about 3 hours of that. I spent a lot of time navigating to try to figure out where the heck we were going. And then I also wrangled children, which is a lot of work. You ate. You always eat. This over the weekend. It's good to eat. It's important. Sleeping also important. So glad to know your basic human needs are being met. Work, sleep, repeat. Nobody drove as much as I did. That's probably true. Maybe. I mean, there are people whose job it is to drive who might have driven as much as me. But driving in Brooklyn and Queens is just miserable. Even on the weekend, there's traffic. So visited family McDonough. Went out with friends. Movie Zootopia. Zootopia was good. London Has Fallen. I haven't seen that yet. I don't have patience to drive or sit that long. Yeah, you can't really afford to think about it. Ooh, Ajwa, are you okay? I'm sorry to hear that. That sounds like, it kind of gives me the, I hope you're okay, but I don't want to think about it very much. I hope that's okay. Yeah, I'm sorry to be freaked out by your malady, but I hope that that you're in okay shape. Well, for everybody who had a good weekend, good. Like it seems like you all made choices that you enjoyed. For those of you who had underwent unfortunate maladies, I'm sorry. I hope you heal fast. We left off last class with some stuff in the middle of a very exciting time because we were talking about the normal distribution, which you guys might not think is exciting, but it is, and you're wrong. So let's what you're gonna need today. I want you to get this if you can. If you can go on to D2L. Yeah. If you go on to D2L. But what I want you to find is here. Let me pretend I'm a student. Oh, I put up the practice exam, by the way, so that's posted. I'll double check it while I'm here. But on D2L, you're gonna want. Where is it? It's in course info and helpful stuff. Let's see if that's where it is. Probability theory, probability distributions. Is this it? I bet it's not it. It's not it. No, not this one. Although that's really handy, by the way. If those of you who've been wondering, like, how do I know which one to use? This is a little chart I made that tells you how to know which one to use. See, this is where it would have been useful for me to find something ahead of time. So where is it? Notes. Exam prep materials. Z distribution table. Oh, it's in the exam 2 prep materials. That's probably the easiest place to get it. So if you go in the exam 2 prep materials, you'll see this Z distribution table. Which if you download it and open it, it will look like this. And you're going to want that for today. You'll see it on my screen. So if you want to copy, you're going to want to print this out, or I'll bring printed copies next class. But we're going to talk about this table. And so I wanted you to show you where it is. It's available in the exam 2 project materials. So you all should have access to that. But the other stuff on D2L is also awesome. So you should go find that stuff too. Okay, so you want to make sure that you have access to the standard normal distribution table. I will give this table to you for the exam, absolutely, and a formula sheet for the exam. But for the practice problems, you're going to want this table. I was going to hand them out today, and then something blew up in the A building, and so I'm not at the A building because if I want to do this, I have to be at home because this is where I have my webcam and all this stuff set up. Okay, in any case, we're going to take a look at this table in a minute. Let me see if I can. Maybe the useful thing to do here would be to screenshot this. Can I do that? This is what I want to do. Can you bring your own formula sheet? Yep, same as before. Okay. Sorry for the delay. I want to copy this if I can. Okay, so we were talking about the normal distribution, and it is a continuous probability distribution, just like ones we've worked with in the past. And I want to talk a little bit about the normal distribution today. So the normal distribution, we said, it had a total, it looked like this. Right? And it had a total area of 1. The center is at the mean, which we use mu to indicate. That's the mean. And then to indicate what standard deviation is, usually we put that up here, right? That's the standard deviation. And that's how we indicate which normal distribution we're talking about. That is our standard deviation. So for example, we might talk about a distribution that has a normal distribution that has a mean of 25. That's a 5. Let's rewrite that. A mean of 25 and a standard deviation of 10. And we talked a little bit last class about how we might care about how far away from the standard deviation something is. Just to recap, let's say you took whatever test this is or got this random variable. You got a 37.5. We learned about the z-score formula. The z-score formula helps us figure out how far away from the mean you are in standard deviations. And so in this case, our x would be this 37.5. And x is always a value on the line, right? That's where this comes from. 37.5. And then our mu is the center of the distribution, which in this case is at 25. And our standard deviation is 10. And so in this case, we would have 12.5 divided by 10, which would be to say you would be 1.25 standard deviations above or to the right of the mean. Okay. And so that's one way we can deal with work with normal distributions. Where we actually left off was by drawing a new standard, a new distribution, or a special case of the normal distribution, which was called the standard normal distribution. The standard normal distribution, I'm sorry, I have a really hard time drawing good normal curves on this tablet, but I'll do the best I can. Standard normal distribution is just the normal distribution with a mean of 0, 0, 0, 0, and a variance of 1. Okay. Mean of 0 and variance of 1, or standard deviation of 1, because the standard deviation is the square root of the variance, and the square root of 1 is 1. And so that is a standard normal distribution. Now, sometimes we want to know things like, what is the probability that a randomly chosen person would score a 37.5 or higher on this test, right? It turns out that if we had a table for every single normal distribution, we would have a lot of tables because there are an infinite number of normal distributions. And so instead, a lot of times what we do is we use the z distribution to relate these to each other. And then we look at probabilities of things happening on the z distribution. So what we can do instead is we can say, what is the probability that we would observe an outcome that is 1.25 standard deviations or higher to the right of our mean, right? And so we could ask this question: how big is this? And so where we're gonna start off today is learning how to measure areas under the curve in the standard normal distribution. So let's look at that case. I'm gonna redraw it. Let's look at our table when it comes to the curve, the standard normal curve, and we want to know about 1.25. So let's switch to the table. Got the table right here. You've got your z table printed already, then good for you. If not, we can all look at it together. But what you can see is table 1, standard normal distribution. We should read this paragraph all together. When you have a table that has this many numbers and very few words, those words are very valuable. They're there for a reason. So let's read them together. Entries in the table, that is to say in the body of the table, give the area under the curve between the mean and z standard deviations above the mean. For example, for z equals 1.25, the area under the curve between the mean and z is 0.3944. So just to see what that means, it says 1.25, which is the number we're looking at. If we go to 1.25, well, how do we get to 1.25? This little z in the corner here tells us that the boundaries here, these things, and these things, these pertain to our z's. And on the left here, you'll see that we have, if you remember place value, we have units. So you can see 1, 2, all the way to 3. And we also have tenths. So over here, we have everything from 0.0 to 3.0. And then along the top, we have hundredths. So this gives us the corresponding area under the curve based on the value of our z. So the area between 0 and z, I mean, it's basically this area here, right? If we're at z equals 0, 0, that's nothing. There is no area because we're just right on this line, right? There's no area there. If we go out to 0.01, which is to say just inch a little teensy bit out, we can see that now the area we have covered is 0.004. Let's say we go out to z equals 1.03. Well, we go down to 1.0 and then over to 0.03, and we would see this number, 3485. That means that if we go one unit over, what chapter is this? Chapter 6, I think, continuous probability distributions. If we go over 1 unit, you talk about the notes, yes, it's 6 continuous probability distributions. If we go over 1 unit, then the area we've covered is 34.85% of the total curve. So that's the size of this area here if z is 1. In the case we're looking at, z is 1.25. And so you can see when we look at 1.25, go down to 1.2, go over to 0.05, we see 0.3944. Okay, so we see 0.3944. I'm going to switch back to my drawing. That tells us the size of the area between 0 and z. So this area here, this area is 0.3944. And if we wanted to write that precisely, we would say the probability that a randomly drawn z variable falls between 0 and 1.25 is 0.3944, right? Because we're still talking about probabilities. And so if there's something that comes from this distribution, the probability that randomly chosen number would be between 0 and 1.25 is about 39.44%. Okay? Now, what is the chance that it would be higher than that? I want you guys to try to think through this. I'm going to keep drawing here while you think through this. How big is this area going to be? And here's a hint, okay, because that's what we really care about. If we want to know that or higher, we know the size of the total area, right? The total area is 1, okay? And that means, and because it's symmetrical, we know the size of this area. This area is 0.5 because it's half of the curve. What I want to know, if you guys can figure out, is how are we going to find the area in the upper tail? Do you guys know how we're going to find the area in the upper tail? I'll let you ponder that for a minute and chime in on Slack when you think you know. 0.1056. That is the answer to the question, what is that area? That is not the answer to the question, how are we going to find that area? So how do we find that area? You guys have the right insight there. But how did you come up with that number? One minus 0.5, okay, which is to say 0.5, right? That's right. Okay, so what we have then is we know that this entire half of the curve combines to make 0.5. And we know that the orange striped area is 0.3944. And so to find the rest of this, we're going to take 0.5 minus 0.3944, which gives us 0.1056. Cool. So that is how we find an upper tail. If we have an area that touches 0, we can just look it up. Sometimes we're going to have some more complicated stuff though, right? So let's say, for example, instead of 1.25 or 0 to 1.25 or 1.25 and up, let's try a slightly more complicated case, not a lot more complicated. Not understanding the area situation, okay? We'll play with it a little bit more, but the total area is 1 because the probability that something will happen is 100%. Because this is symmetrical, the total area is 1, that's right. So the total, because area, remember, what we're talking about is that area is probability. So area equals probability. And so the total area is equal to the total probability. And the total probability has to be 1 because that's what the 100% chance something is going to happen, right? And that's what we have here is a picture of all of the things. That's the probability of the sample space, right? The probability of the sample space is 1, which is going to be equal to the total area. Now, if we split this down the middle, we get 0.5 on each side. So that's because we're splitting it in half, right? So that means we get 0.5 over here and 0.5 over here. There's a 50% chance we're going to get a positive value and a 50% chance we're going to get a negative value. Now, if we want to know what the probability is that z is greater than 1.25, well, we know that there's a 50% chance it'll be positive. And that's right, it's supposed to be half. My drawings are going to be a little... they're supposed to be symmetrical. So the probability that z is greater than 1.25 is the probability that z is greater than 0, which is 0.5, minus the probability that z falls between 0 and 1.25, which we could look up. And that's this thing here, the 0.3944. So 0.5 minus 0.3944. Cool? I hope that makes sense now. The 0 is the halfway point. In this case, that's right. In a different normal distribution, whatever the mean is, right? The mean is the halfway point. So you've got mu, and then the halfway point is the mean. In this case, awesome. Glad to hear it, Therese. Okay. Let's say, for example, instead of 1.25, let's say we want to know about negative 2.17. Let's say we want to know the size of the tail over here for negative 2.17. Okay. So now we can go back to our table. Let's see if I can do this so we can still see her. Yep, we can. Okay, so I can still see negative 2.17 over there. Now, it turns out this table only tells me about positive numbers. But what do we know? Well, we know that this is symmetrical. So if I look up positive 2.17, that puts me right here at 0.4850. And that 0.4850 is the area between 0 and positive 2.18 or 2.17. So this is 48. I fit it in here. 4850. Okay. That's what the table tells me. And I want to be clear about this. That's all the table tells me about. It just tells me about areas shaped like this. It's just a table full of numbers of all of the different ways you can make a shape starting at 0 and ending at some positive value. So how, hey Abu, welcome. So how can I find this area over here? Hey Abu, it's Abu in... Sorry, I'm not sure if Abu's in general or not. I didn't see his message pop up there. Abu, you want to join #general if you just jumped in. Tell him there. Sorry about this, guys. Just want to make sure everybody's in the right spot. That's right. Because it's symmetrical, we just invert it, which means that if this area that I outlined is 0.4850, that also means that this area right here is 4850, right? Because of symmetry. Essentially, you don't make the area negative because areas are never negative, right? The way that the metaphor that I like to use is I like to use this as like a street address. And you could have a negative street address, by which you mean like north or south, right? Or east or west. But then this area, this thing up here is sort of like lot size. You would never have a negative quarter acre. I mean, unless you owe somebody land or something. But you could never have a negative quarter acre. But if you went to, if you figured out, if you had a house that started at 0 and went to south 2.17, you might have a lot size of 0.4850. If you had a lot that started at 0 and went to north 2.17, you would also have 0.4850 of an acre, right? So that's kind of how I mean that, right? It's just it's a symmetrical plot of land. How much have you covered? Well, you've covered 48.5% of it if you go 2.17 standard deviations in either direction. Okay, well, if this area is 0.4850, then how big is the lower tail? Well, now we can use the same logic we used before, right? The total area here is 0.5, and so this area here is going to be 0.5 minus 0.4850, which I'll let you guys tell me what that is as you figure it out. Yep, that's right, David. What does that equal, though? I'll let you guys give me the answer. And then in the meantime, while you guys are doing the arithmetic there, we'll set up a slightly more complicated example. 0.015, I think that's right. Subtract by 1. So if we subtracted by 1, it would give us all of the rest of the area. It would give us this tail, but it would also give us this whole area, right? It would be, because that would be the complement of the area we've identified. Take 1 0 away. Yes, that's right, 0.015. So we only want to take, we only want to subtract the part that actually makes sense, whatever the part that is related there. So 0.015, you guys say? I think that's right. There we go, 0.015. Okay, let's look at a slightly trickier example. This one's not super tricky. Actually, we'll use some of the numbers we already know to make this a little bit more straightforward. Oop, that's a terrible drawing. Let's say that instead of wanting to know about the tails, let's say instead we want to know about the interior. So let's say we want to know, and the way you would write this in math language is the problem. Nice work, Noah. Welcome, Noah. If you guys are here and you haven't said hi yet, chime in just to let me know you're here, just so I can say hello to you. I like to say hello to you. I will say it's an interesting challenge to see A. Twenibo and be like, oh yeah, that's Ajwa, and to see N. Kabeta and be like, oh, that's Noah. Like, how well do I really know your names? Do I know them well enough that I can see a first initial and a last name and be able to know your first name? It's an interesting quiz. You are indeed, Noah. Welcome. So what is the probability that Z, that we would draw random Z? Hey, how's it going, Azalea? What is the probability that we would draw a Z from this area? Okay. Any guesses as to how we're going to figure that out? The tip is we're going to use a table, right? We're definitely going to use the table. And we can use the values we already looked up on the table. So let's remember, we already looked up 1.25. Hey, Sarah. Double the table's result. That's a good guess. Eli's got the idea. Yeah, 2 scores. That's right. So we already got Z and positive 1.25, right? That was, I don't remember what that was. What was that? 3944. No, we're not subtracting by 1 now. We're gonna do very little subtracting by 1, as it turns out. Every once in a while we would, but not necessarily. Given just because of the shape of the table we're using. But this area here, we already looked up, right? The area between 0 and 1.25. No, don't be quiet. No, absolutely not. That is absolutely the wrong approach. I'm very delighted to hear your questions. So please keep chiming in. Because when you tell me something and it's almost but not quite right, it means that I have not been clear. And that is incentive for me to be more clear. And if you're quiet, then I'll just keep being unclear. And if there's one thing I dislike, it is continuing to be wrong when I'm wrong. I want to stop being wrong as fast as possible so that I can feel like I'm right all the time. So Brandon, that's close. That would be if it was between negative 2.17 and positive 2.17, but it's not. It's between negative 2.17 and positive 1.25. So we have 2 different values here. The first one is between 0 and 1.25, which we looked up, 3944. The second one is between negative 2.17 and 0. Yeah, my drawing makes it look like it's more symmetrical than it is, so that might be part of the confusion. But that's good. I want you to be a little confused because that way it forces you to learn. If you don't feel confused at all, then you figure you just know everything, and that's bad. It's a good situation. It's conducive to learning when you feel slightly confused, but not totally. I think you want that first one to be no. I think it's just get rid of the 1 minus. Yeah, it's what Becca's right in there. It's so I'll write it in math in a second, but it's 0.4850 here plus the 0.93944, right? Because you can see how combining these 2 shapes, we would get the shape we want. So we can add those together if we want. But let me lay it out a little bit more formally for you so you can see. So if we want the probability of negative 2.17 less than Z less than 1.25, what we can do is we can break that down the mean line, right? 2.17 is less than Z is less than 0, plus the probability that 0 is less than Z is less than 1.25. Now, the second part here, I should have written in blue because this is the blue one. We could just look this up. This is 0.3944. Yeah, 3944. Actually, let me write it 0.3944. This first one is negative, but it turns out because of symmetry, it's the same as 0 less than z less than 2.17. Yeah, that's right. Go Becca. Go Becca. All right. And here we get 0.4850 when we look this up, right? So now we have the parts we need. 0.4850 plus 3944. If we add those together, what does that equal? 4, 9, 9 plus 8 is 17, carry the 1. 4, 5, 6, 7, 8. 0.8794. Somebody double check my math there. I think that's right. And so that would be the probability that a randomly chosen z variable would fall between these two values. I will say, if this feels like it makes your eyes roll back in your head a little bit because it's technical and what possible application does this have, that's not core math. It's core enough. We could back it up if you guys feel like you're struggling with addition, but I think it's good enough for now. 0.8794. So there's an 88% chance roughly that it would fall somewhere between those two. Cool. So that's pretty good. Let's do one more. I was starting to say, I wrote all that to essentially say 0.3944 plus 4850. That's a good point. But I wrote all that essentially to produce an argument for why it is 0.3944 plus 0.4850, right? Because what is this 0.4850? Well, that is the probability that z falls between 0 and 2.17, which I can look up on the table, which is also the probability that z falls between 0 and negative 2.17 by symmetry. Now, if you feel like you're comfortable enough to just jump to conclusions, that's awesome. But I don't feel comfortable yet. Why am I adding them both? Because this area, the blue area here, is 39%. The green area here is 49%. And I want to know what the chance is that you're going to get the whole thing. Yeah, because we have two z-scores. And so we're looking for, we're breaking this big area we totally care about, right? This big area we want to know for whatever reason. And we'll get into why we would want to know it in a little bit when we start to get to applications. This golden area, we want to know how big this is. How do we find out how big it is? Well, we break it down the middle, and then we find the two parts. And if you take, an example would be, let's say we wanted to know how many calories a salad with almonds had in it, right? What we could do is we figure out how many calories the greens have in it, and then how many calories the almonds have in it, and we add those together. But then we mix it all together, and we just eat the salad. And that's what we're doing here. We're breaking it into two things that are relatively easy to understand in order to figure out this more complicated thing, which is combine these areas. In principle, what we've done is we've taken the union of these two areas that had no intersection, right? So we're taking the probability of the union of these two mutually exclusive things, which we talked about previously. Cool. I'm glad it makes sense, Lisa. Okay. That's a little bit more complicated one. Obviously, we're getting some good questions. That's great. Let's do the last one that I want to do, because I think this covers like every possible salad reference. You guys can play now, you're not allowed to play a drinking game about how many times I refer to salad, but you could. It probably would be not many. I don't eat a lot of salad. Let's say that we had 0.83 here, and then we had 2.32. I'm just making up random numbers. And we want to know how big this area is. Now, this is a little bit trickier. And I'll say, like, when we want to know whether we should add or subtract, the truth is we should do whatever we have to do to find an area, right? And so there's not like a rule of thumb. The easiest thing to do is to draw a picture and understand the picture, okay? To use your ability with spatial relations to practice that until you kind of get this stuff. So let's say we want to know the probability that a randomly chosen z variable falls between 0.83 and 2.32. Well, it turns out that we can take intersections to try to get this, right? This time, instead of writing the math after the fact, I'm going to break it down ahead of time. So it turns out that we can't look up this probability, the probability of a z falling in this range, but we can look up between 0 and 2.32, because the type of table we have is what I call a 0 to Z table. It tells us the probability between 0 and Z. There are other kinds of tables, but they all contain the same information. All Z tables contain the same information. And if we look this up, what are we going to find? You guys look up 2.32 on there and tell me what you see. So if you look up 2.32 in the table, if you have a table, maybe I'll make mine a little more visible for you so you can see it. So you can look for 2.32 there. So take a look on that table and see if you can find 2.32 and tell me what you see. Okay, got 2 people saying 4898. People agreeing with that? Is that the consensus? Oop, I'm drawing the wrong area here. That gives us this area here, right? And you guys are telling me that this is 4898. 4896. 4896 is 2.31. But I said 2.32, so we're gonna stick with 4898 because that's this number right here. Right? Okay. You were close, off by a little bit. It's easy. They're right next to each other. So this is 4898, but that's not the area I want. In fact, hopefully from the picture, you can see that is not only do we know that it's incorrect, we know that it's too big, right? We can look at the area that we've accidentally counted that we don't really want, right? This area right here is not included in the orange stripy area we actually care about, right? This area right here we would like to get rid of. The area we really care about is just this area here. And so this is the area we care about. But the blue area is an area that's included in the 48.98% that we want to get rid of. And we could give that area, the blue area, a name. I don't want pink. A blue area is the probability that a randomly chosen Z will fall between 0. It's not quite that, David, because that's between negative infinity and 0.83. So that's going to be off by 0.5 because that includes this whole half over here. And we don't want to include that. We just want the area between 0 and positive, that's a terrible less than sign, positive 0.83. Again, this we can look up on our table. Do you guys see this on the table? I see it there. I want you guys to tell it to me, though. To be minus, not negative. Okay, so 0.2967 is what somebody's saying, Eli's saying. Thank you, Elijah. And it looks like that's right? We go to 0.83, and we're seeing 0.2967 here. So here we have 0.2967. If any of this is not clear, guys, please chime in. I'm hearing some good answers. I don't want a false sense that people are keeping up if this stuff is confusing. And it is a little confusing to play with these areas, but what we're doing now is mostly just technical skills that we'll be applying soon. Okay, so once we know that the bigger area is 0.4898 and the smaller area is 0.2967, nice work, Abu. What we can say is we need to chop off this bottom 30%, right? So ultimately, if we want to get this pink area, we take the bigger area, 4898, and get rid of the blue area that we don't want, which means that what we need to do is subtract this area now. So we're going to take 4898 and subtract the 2967. 8 minus 7 is 1. 9 minus 6 is 3. We're going to need to borrow by taking one of these tenths and moving it over to the hundredths to make it 10 hundredths. 18 minus 9 is 9. And 3 minus 2 is 1. And what we get now is 0.1931. And that is this area here, 0.1931, which is also this area here, 0.1931. 1831? Did I screw that up? I think I got it right, but I'm anxious about that because I'm bad at stuff sometimes. So let's do it in Excel. New sheet here for calculations. Let's see, you said we had 0.4898 and we had 0.2967. I'm going to take this minus this, 0.1931. Okay, I'm more confident now. So Luisa, it looks like just a carrying error probably. Cool. I actually got it. Awesome. Okay, we're on the same page. So those are kind of the ways that we can run into, those are the ways we can measure areas underneath, just to be clear, right? So to kind of draw just kind of a few intuitive pictures, the table only and always tells us about shapes like this. I'm trying by the hip. I will say I have it open most of the time. It's a pretty useful program. Okay, so it only tells us about areas like this. And then what we can do is we can use the total area is 1. Okay, that's a good question, right? If you added them, then subtracted by 0.5, that would give you the rest of the area. So if we if you added them, that would give you the white area here as well as the area over here that's symmetrical to the blue shaped area. And then if you subtracted that from 0.5, I don't know what you would get. No, you wouldn't add them and subtract from 0.5. And I'm not sure how to explain it other than to say, like, no, you wouldn't. What you do is, in general, if you want just an intermediate area, right? So if you want an area that's shaped like, let's say we could do it over here, right? You want an area shaped like this. What you have to do is start at the middle, right? Measure out to the edge, and then start at the middle again, and then measure out to the middle edge, and then subtract those to get the difference. I know that's not a great drawing, but hopefully that clears it up. That's how you measure those differences to try to get that area. Because you can imagine what you have is you have a bigger piece, and then you have a smaller piece, and you're just finding the difference between those two to find the remaining amount. Yeah, hopefully you can see that with this here as well, right? What we're doing is we're taking, if you look at a number line, let's say we're at 0.83, or, we got 0.83 here, and we've got 2.32. If we want to know, okay, cool. We want to know the probability of this area. We take the probability of this whole area minus the probability of this area to get the probability of the orange part, because that's what's left. Okay, hopefully that clears it up. So in any case, it only tells us about this shape of area, and then we use the total area equals 1 and symmetry and logic, right? This and this and this and shape, like spatial relations, to try to figure out all the other areas we need. Okay, now this is not in and of itself super useful because it's just a technical skill, but it is one of the crucial skills that we need. So how do we solve normal distribution problems? We're going to talk about the 4 steps for normal distribution problems. And I'll say, using the table is a technical skill that feels complex and complicated at first, but eventually becomes one of the easier parts, just because it's just a technical skill, like addition or subtraction. And you guys probably feel like addition or subtraction is pretty easy now, even though my son, who's 5, struggles with it. But eventually that's easy, and then thinking about math in the abstract continues to be the hard part. So the 4 steps for normal distribution problems. The first one, step 1, is to turn your question into a picture. I know some of you had some blurry issues. Has this been okay for you, or have you been able to work that out? Hopefully you can read this. I'm trying to write big enough that you'll be able to see, even if it's a little blurry. Turn your question into a picture. In that case, what you'll have is you'll draw yourself a normal distribution, and then you'll try to label it as best you can. I don't know what your GPPD means, but cool. But I think that's a good thing. You want to label all of these parts that you can, some area in here. Oh, I see. Yeah, that makes more sense. So it'll always give you 3 of these 4. Oh, hi, Emma. I'm glad you're listening. Welcome. It'll always give you 3 of these 4. And then essentially you can think of this whole process as one big logic problem to try to find the 4th one, right? These things are connected tightly in a logically necessary relation. And so if you know 3 of them, there's only one possible answer for the 4th one. And that's what we're engaged in, is the process of figuring out how to find that. Now, usually mu and sigma in this case will not be 0 and 1. They'll be given by the problem some other way, or by the real world in some other way. And so what we need to do is we need to take, in step 2, we need to relate the picture we drew to the standard normal distribution. Now, because this is the one we have a table about. We don't know about the distribution they give us, but we do know about the standard normal. And so we're going to relate it to the standard normal distribution. The way this works is we take the drawing we drew, and then underneath it, we draw another drawing. Ooh, that's a terrible. Again, we draw another normal distribution. This one is the z distribution with a mean of 0 and a standard deviation of 1. And this is z, and this is x. Yeah, p is going to be some probability or area in this case. The mean is always the midpoint. That's right, Azalea. The mean is the midpoint. It's the mean, the median, the mode are the same for normal distributions because it's a symmetrical distribution, unskewed. Okay, once we've related it to the standard normal successfully, we'll practice with this a bunch of times, so don't worry if this feels a little vague right now. We'll either end up with a z or p, a z or an area. So we're going to use z to get p, to get some probability, or p to get z. And that's step 3. So essentially, if we have a z, we're going to use our table to go above the curve, and if we have a p, we're going to use our table to get above the the horizontal axis to find the area, to go from z's to areas. If we have an area, we're going to use the table to get below the axis, and that's what happens in step 3. Essentially, we try to flip to the other side of the axis, and then we end with step 4. Usually, by this point, it feels a little bit like we're in the weeds, and so usually it helps to answer the question. So we reread the question, and then try to figure out, okay, so what was the thing we needed again? And then we try to answer that. So let's do a practice problem. I'll pull up, where do we have some practice problems? You guys have a problem set on this already, right? And I think some people struggled with it because they were kind of tricky. So let's look at the discrete and continuous problem set you just had. Oh, let me move this out of the way. Some people were having trouble with this last one here, which makes sense. I kind of wanted you guys to try to take a look at the notes and try to figure it out. But today we will relieve that sense of frustration. So here we had the U.S. Bureau of Labor Statistics question. I'll make this bigger so everybody can see it once I feel like everybody's had enough time to write down the last step. Here we go. Oh, not that one. This one. No. That's uniform. This is the first normal one. Okay. So number 634. You guys struggled with this a little bit, I'm guessing. If you did. Salad example is key. Do I have salad examples here? I don't have any more. U.S. Bureau of Labor Statistics reports that the average annual expenditure on food and drink, maybe that's the salad there, for all families is $5,700. Assume that the annual expenditure on food and drink is normally distributed and the standard deviation is 1,500. Part A, what is the range of expenditures of the 10% of families with the lowest annual spending on food and drink? Okay. So here we can see that now we're talking about those people that don't spend a lot of money on food and drink. And we can draw a picture of all of the families that are covered in this survey. Right? We can draw a distribution of all of these families. So we want to know what is the range of expenditures. In order to do this, we're going to start with step 1. Step 1 is to take our question and turn it into a picture. In this case, we know that this picture is a normal distribution. In other cases, it might be a uniform distribution, in which case we would draw the rectangle we talked about last class. In other cases, it might be the exponential distribution. But in this case, it's a normal distribution. And let me make this a little bit bigger so that we feel like we have plenty of room. Step 1, we need to label this. The question gives us our mean. It says the average annual expenditure is $5,700. And the standard deviation is 1,500. How do you know when to use which? In this case, it specifically says, assume that the annual expenditure on food or drink is normally distributed. Whereas the previous question, for example, says, assume that the probability distribution for minutes of programming can be approximated by a uniform distribution. So it just tells you which to use in this case. Cool. So that's how we know. It tells us which to use. Because the reason it tells us in these cases is that almost nothing in the world is actually uniformly or normally distributed. And so we have to approximate it. We're just assuming. We have to make an assumption. It's not a good assumption, but we're making it anyway. Okay. So now, cool. Good. Glad to hear it, Delma. Now it wants us to know what is the range of expenditures of people in the lowest 10%. So since it's giving us an area, it's telling us that this lower area is 0.1 because that's 10%, right? And it wants to know, what is this? What is the dollar cutoff, essentially, that would put you in the bottom 10% of families in terms of expenditures on food and drink? Cool. And so that is step one done. We've labeled the 3 of the 4 that they give us. They gave us a mean, they gave us a standard deviation, they gave us an area, and we still need some particular value of X. And that's what we're going to try to find out. Step 2 is to convert this to the standard normal, or to relate this to the standard normal distribution. So this distribution is a distribution of X, where X is expenditure on food for a randomly chosen family. So that's the random experiment, is choose a family. How much do they spend on food and drink? This curve is our Z distribution. And our Z distribution, whoop, that's a terrible Z distribution. The normal distribution with a mean of 0 and a standard deviation of 1. And in order to continue relating this, I need to label 3 of the 4 things again. Now, if I've related this successfully, if I've drawn these like as successful analogies, this area here should remain 10%. And then this should be the Z-score that corresponds to my X up here, right? So these two things are related. This Z and this X should come from the same place, right? Essentially, we're going to have an imaginary family that is exactly on the cutoff point, and they're going to have a dollar expenditure, and they're also going to have a Z-score, and we want to relate those to each other. But that's step 2 done, right? Now we have 2 drawings. They're analogous to each other, right? So they look parallel. Step 3 is to use P to get Z or use Z to get P. Okay, so in this case, I have an area. I need to use that to find my Z. We hadn't tried this actually with the Z table. So this is new. We're going to learn something new. It turns out that we can go the other way on our Z table. So hopefully everybody's had a chance to digest that Z drawing, at least a little bit. What we can say is, if we have a Z score, we can use that to find an area. But if we have an area, we can use that to find a Z score. So we want to look in here to try to find ourselves a Z score. Or to try to find ourselves the area. Now, in order to do that, we need an area that is shaped like this, which, going back to my drawing, means that I need to do whatever it takes to find an area shaped like this, okay? So I need to find a good area that will help me answer my question that is shaped like this. Now, I'm not going to be able to find this Z because it's negative, and that's not going to show up on the table. But what I can do is I can find its opposite. So when I'm writing negative Z here, I just mean the opposite of my actual Z, which is a negative number. Does that make sense? So I need to find the opposite of my Z, my additive opposite. That's going to be on this table. But in order to do that, I need to take advantage of symmetry, right? So if that tail is 0.1, that means this tail is also 0.1, but I can't look up 0.1 on my table, okay? Instead, I have to find the area of this striped area. So how am I going to find the area of that striped area? That area is the area we're going to look up in the table. But first, I need to find it. So how big is this striped area going to be? Let you guys ponder that for a minute. Once we find that area, it turns out that we can look in the body of the table for areas and use them to back out a Z. Like, for example, if we figured out this orange striped area was 19.5%, we could say that Z must be 0.51, okay? Similarly, if we found out, yeah, that's right, Elijah. Can you explain how you got that? If we found out that that area was 17%, then we would know that our Z was 0.44. So how did you guys figure out that that's 0.4? Well, it turns out that the tail is 0.1, right? And that tail plus this orange striped area have to be what? 0.5, that's right. Because the orange striped area and the tail combine to make 0.5, we can say that this area here is 0.5 minus the tail, 0.1, which is 0.4. Dalma, I think you have that backwards, but yes, that's right. So this area here is 0.4. Cool? Okay. So since that area is 0.4, we can use that to look up our z. Now, if you look on the z table, what you'll see is that 0.4 is not in the body. We're looking for 0.4 in the body, right? Because this is an area. So we're looking for 0.4. And here I see 0.3997 and 0.4011. I think 0.3997 is as close as I'm going to get. So that 0.3997 is pretty close enough. And that corresponds to a value of 1.28. So that means that my z over here, this z is 1.28. That is to say, if I had a family that was 1.28 standard deviation to the right, they would be at the top or the very bottom edge of the top 10%. But that's not my z because my z is negative, right? So instead, my z is equal to negative 1.28. Okay. Cool. So my z is negative 1.28. That is step 3. Sometimes step 3 takes a little while, takes a little bit of intuition. That's the part where we're using our table, right? In this case, we had to back out a value of z. And just to re-go through the steps again, what we said was our lower tail is 0.1, but we need to find an area between 0. Cool. I'm glad to hear that's helpful. Our lower area is 0.1, but we need to find an area between 0 and z that will help us. And so what we can do, if the lower tail is 0.1, that means the upper tail of the positive version would also be 0.1. Okay. And if the upper tail is 0.1, the top half is 0.5. So we can use 0.5 minus 0.1 to get 0.4. And so a lot of times if we have a lower tail, we're going to need to subtract from 0.5 to get that area. Another way to think about it would be we could subtract this 0.1 from 0.5 to find that this area is 0.4. Okay. And then we could look up 0.4 in the body of the table and see 1.28. That's right. So z is negative 1.28. But that's not x, because x, if you remember, is the number up here. So x is in dollars. But that's right. So negative 1.28 is the value of z that we have. That's because if we want to start at 0 and go down 40% of the area, the table tells us here, actually the table tells us it's 39.97%. But that brings us to 1.28. And since we're moving to the left, it's negative 1.28. If we were moving to the right, it would be positive 1.8. So that's step 3 done. Step 1, again, draw the drawing. Step 2, relate to the standard normal. Step 3, mess with the standard normal until you have both P and Z. So if you have one, you got to get the other one. And as I said before, often we spend our time in the weeds, or we end up in the weeds after step 3. So now we have to ask ourselves the question again. What is the range of expenditures of the 10% of families? Cool. I'm glad that's helpful. I'm glad it worked out, Azalea. What is the range of expenditures of the 10% of families with the lowest annual spending of food and drink? That's right. We weren't just talking about normal distributions. We're talking about people spending money on food and drink, spending not very much money. And so we need to convert this into dollars. And this is where we get to the one thing we're always going to use before we're done. We haven't used it yet. That is the score formula. If you remember the score formula, it was z equals x minus mu over sigma. And this relates every normal distribution to every other normal distribution. Once we have 3 of the 4 of these, we can use algebra to get the last one. So we've got negative 1.28 equals x minus 5,700 divided by 1,500. And I'm just plugging in numbers from the table above, right? So we've got negative 1.28 here, x is unknown, 5,700 is right here, and 1,500 is right here. Cool? Now we need to solve for x. If we solve for x, we'll get the dollar amount that puts you right at the edge there. So the way to do that is with algebra. 15, multiply both sides by 1,500. And I'm not going to multiply it out. I'm going to keep them next to each other because I think it'll be clear what we're doing when I go back to the drawing. So negative 1.28 times 1,500 equals x minus 5,700. Now to find x, I need to add 5,700 to each side. Add 5,700 over here. And what I get is x equals 5,700 minus 1.28 times 1,500. Cool? Now I can calculate that, and I will calculate it in a minute. But first, I want to draw your attention to the structure, because that structure of this has logic in it. It says, if you want to know what the value of spending is, that will end you up at just the very top edge of the bottom 10%. You start at 5,700, okay? Now, looking back at our curve, we can see 5,700 is in the middle. So it's almost like a treasure map. It says start at 5,700. And then it says move to the left. This negative sign says move to the left 1.28 standard deviations. And looking down here, you can see move to the left 1.28 standard deviations. So we're going to go to 5,700, and we're going to go 1.28. So this is 1 sigma, 1 standard deviation. And then we're going to move another standard deviation, or another quarter, roughly, standard deviation. So we're making a big jump of a 1 standard deviation jump, and then we're going to move another 0.28 standard deviation jump. Okay, well, that tells me where I am in Z's, right? I'm 1.28 standard deviation to the left. Where am I in dollars? Well, 1 standard deviation is $1,500, and then we have to multiply that by 0.28 as well. But that's how this tells us how to get there, right? It's telling us to move to the left 1.28 standard deviations, each one of which is $1,500. And so that's what this is telling us. Yeah. Okay, so what does that turn into? Trust the Excel spreadsheet again. 5,700 negative 1.28. 100. And multiply these. We'll see that we want to move $1,920 to the left. So we're going to do 5,700 minus 1920. And I don't need to Excel for this, or I don't need a calculator for this. 10, 9 minus 2 is 7. 6 minus 9 is 16 minus 9 is 7. 4 minus 1 is 3. 3770. Double check that. Cool. 3780. I did something wrong. I did need Excel after all. Good thing I had it. Okay. So 3780. That is the dollar amount that families in the lowest 10% are spending, which is to say 3780 or less. Since the question was asking for a range, what range of expenditures, we can say the 10% of families with the lowest annual spending on food and drink spend $3,780 a year or less. Cool? Cool. So now we can answer questions, useful questions about things like average annual expenditure and stuff like that. Excellent. Okay. Let me see what else I want to talk about today. I think that's it. We have one more probability distribution to learn before we get to the exam, and so we'll learn that next class, and we'll take a quiz on this stuff to make sure it's locked in. But I don't want to start a new section when we have roughly 9 minutes of class. The timing just happened to turn out that way. But I will say I'll stick around for the next 9 minutes or so. If you guys have questions, you want to hit me up on Slack, feel free to do so. Hopefully you found this useful. If you want to give me feedback on whether you feel like this works, I will say one thing I think this is very useful for, and I've had some success with it, is working with other students. Yes, we do have a quiz on Thursday, Lisa. We should take an online quiz and do this online again. Okay, so you like online stuff. Next Tuesday is the exam, so we're definitely not going to have a quiz on the exam day. But we do have a quiz on Thursday. But yeah, it's very useful to do this on one-on-one. If you have a project question, you don't need to come all the way to campus. I don't need to go all the way to campus. We can work it out at a distance. So I'm happy to help out there. I hope you guys found this useful. Again, if it was terrible, let me know and we'll never do it again. I don't know how to know if it's terrible or not because I can't see it from your perspective. So you have to tell me if it seems terrible. But yeah, I'm happy to answer any questions, and I'll duck off the webcam, but I'll still be on Slack. So, is it possible you can record a video about this like all the others? I'm pretty sure there is a video about this already posted. So salad with almonds, indeed. Yeah, there is a video of this. It might be in the review of business statistics playlist. Actually, how about I just post it in Slack right now because I'm on my YouTube channel. I posted on Slack. What are the due dates again? You want me to pull that up? Here, I'll put that back up for you. There you go. You can see the due dates. And then Noah, that's a good question. So let me see if I can. It was pretty awesome. Ray liked it. Cool. Well, I'm glad you approved. Let's see. I do have a video about this stuff, but it's old. Just, I mean, it's just been around a while. But normal distribution stuff is stuff that I've had for a bit. But yeah, I'm happy to do this. And one-on-one, as I said, I'm happy to do that as well. It's nice because then you can drop your spreadsheet in Slack. I can open it on my computer and show you, as I walk through it, you can see what I'm doing, and I can, be talking to you. We can also do it with voice chat, so I can hear you as well. You're very welcome, Azalea. I hope it was useful. Yeah, if you guys are done, you can go. If you have more questions, you can stick around. Either way is fine. Let me see if I can find a playlist for you, Noah. You're welcome, Lisa. Copy. Where'd Slack go? Okay, I'm just so you know, Noah, I'm pasting the Slack playlist or the YouTube playlist. Now, that playlist has proof can work a webcast. Awesome. I'm glad that somebody enjoys this. Yeah, not everybody can do this, I guess. I don't know. It doesn't seem that tricky to me, but it's not nothing. So in order to answer your question, Noah, the normal distribution intro is there, number 3. The last 2 videos there are the ones. I'm really glad you liked it, Ajwa. The last 2 videos there, how to find the area under a normal curve and the normal distribution practice problems, number 10 and 11 on that playlist are the ones that look like this. And this is weird, but you can watch a video of me talking. Hey, there you go. See? So this is what the video looks like. And you can see I did a different problem, which I think is one of the ones you have to do for your next practice problem set. See if you want to see me do a problem set there. You can see the method hasn't changed that much since the time I recorded this. Cool. Maybe next time I should just open this up and hit play, and then you guys just watch it together. But yep, so you can watch a video like this. I'm not sure what happens to the live broadcast. I think it turns into a video. And so once I find out what happens with that, I'll let you all know. Cool. Any other questions? You're very welcome, Noah. If you have any other questions, let me know, and I will. Not sure whether there's poop on that snap of snap, but yeah, let me know, and I'll respond to you before we go. We should do this more often. I'll take that under advisement. Cool. See you, Abu. Have a good time at work. More salad examples, please. I'll see what I can work in. Maybe I should reach out to like Fresh Express for like what product placement. Maybe I can get like royalties anytime I drop a baby spinach reference. All right, guys. Thanks a lot. Like I said, the practice exam is posted. Let me know if you have any questions, you need any help, and I'll be happy to help you all out. Check you later. I'll still be on, but I'm just going to hide my window. So